thought, but we needed somebody who really knew what they were talking about to confirm. But let's wait a second for more people to join.
I definitely have figures in other notebooks that I could probably insert into that one for future reference.
Okay. Well, I've been modifying notebooks with typo fixes and things as we go along, as people mention things, and I've been reposting to GeoSync. So, and in fact, for the next lecture, which I believe is on the offsets, isn't that next, or what's next?
It's David next, I think.
I'm just checking. Hold on. It could be David's next. Thursday. Yeah, David's next. Right. So at the end of, at 1 o'clock, we'll have the offset stack for velocity dynamics. That is a completely new set of modules, which in your current instance will not be present until you stop the server and restart the server, which is not the same thing as logging out and logging back in again. So if you want, and that one I think is interactive and does some processing. So probably a good idea to do it. Somehow my screen just went blank. I don't know why. You can still hear me though, right?
Right. We have your cartoon avatar speaking to us.
Interesting. Because I never loaded that into Zoom, but that's okay. Somehow it got there.
Zoom is clever.
Very interesting. I wonder what happened. All right, it's on my laptop screen, but not on my big screen. I don't know, the connection somehow disappeared. Okay, we're up to 45. I guess we can get started. I think the person who asked that question about look vectors, though, is not on. I think it was Deha. Oh no, it was Jay Kim, actually. Is he on?
I don't see him yet.
Yeah. Okay, well, so neither are on. We can just talk about other things first. Anybody have any questions or want to show any results?
Can I just ask a quick follow-up on you said there were updated notebooks. I see an updated notebook for section 4.4, the offset stack that you mentioned, but I don't, my 4.1, 4.2, and 4.3 are still empty. Is that just going to be lectures?
Well, that's a good
That shouldn't be. But mine are also. I don't know. Well, 4.1 is mostly a lecture, right? I think.
Yeah, so David emailed me just about an hour ago saying, I'm going to miss the 10 o'clock and I'm working on the lecture up till the last minute. So I think he's revamping whatever we did previous years. And that is probably going to be just a lecture. I think 11 is usually a lecture. And we will eventually put it into that folder. And it's possible that the second segment is also a lecture. So.
Okay.
Yeah, and just Gareth, for your information, I've got to go on lab to give a tour to some person from High VIP at 2, but I'm carless, so I have to walk in, and that takes a while. So I'm probably going to drop off around 1, unfortunately, since I really wanted to hear Brian's lecture. But that's just the way it is.
Well, there's always the video.
Yes.
Hey, Gareth, just a quick question on the data. If we download from ASF, like if we have like a bounding box within ASF and download it, would it just download that particular bounding box or the whole acquisition?
The whole scene cover that intersects with that bounding box.
Okay.
Sometimes there'll be more than one on the same track that will, and you might want to download both of them.
Okay.
But you have to actively choose to download them, usually.
Okay. Yeah. I think, I mean, I just put the link, the way you showed me how to put that link. I used that to download, but it looks like what I'm seeing on my notebook is just like my bounding box, my AOI. That's the only thing I'm seeing, but I'm just I'm still trying to make sure that that's correct. But
That's
yeah.
not true. Almost certainly not. The files are large. They're like, I don't know, 4 gigabytes per SLC, or some up to 4,
Okay.
4.5, and that covers a very large area. So if the files are that big, they're going to be covering an area that's like 250 kilometers across by about the same in the along track direction.
Okay.
So yeah, you can tell from the size of the file how big the scene is.
Okay. Okay.
Like if you looked at the size of the Atlas data we were processing, it's much smaller, even after it was focused, maybe a third of the size.
Yeah, I'll double check what I'm seeing on that notebook. Thanks.
Pulls back.
Yes. I don't know what I did. Other questions? We had an instructive dialogue this morning in the office hours about the orientation of the imagery that you see, the interferograms and SLC imagery. That often, when you're new to this, is a little confusing. So, you know, if you have an area of interest and it's geographically, it looks like what you're accustomed to from looking at a map. When you look at an ascending image, you may see it as looking different. And it even looks different from the descending image in the ascending, or vice versa. So maybe have people experienced that? Have you noticed that the imagery has a different orientation? Can anybody other than Alex Sarmiento, who asked the question earlier, comment on what you observed? And do you understand why you observed what you observed?
I mean, I'm trying to understand, like, I'm exactly what all this saying, I'm exactly having the same issue. That's why I asked Gareth, like, what am I seeing here? And
You want to share your screen and we can walk through it?
okay, well, awesome. Thank you. I'll do that. So, this is, I just replaced whatever Harish had with my, and this is the plot of that SLC. I'm opening this on my, so I should have done this. For some reason, I'm having issues with ASF while using baseline tool for the ALOS data sets. And it's I think Franz is looking at that, but
yeah, we now know why.
oh yeah. So yeah, this is this is the area. This is my yeah, this is what I was talking about, and this is what I got from using the same scene, and yeah,
Nice and elongated.
yes. So this is what I should expect, right? I mean, this is yeah.
So that's one swath.
It's a strip
Sorry,
map
one
scene.
sub-swath. Sorry, it's one sub-swath.
It's a strip map scene, I think.
Yes.
Oh, we're doing ALOS. I'm sorry. Yeah, strip
Yeah.
map. Okay, very
Yeah, I
good.
think this is a PLR data set, a polarimetric data set, so it's very narrow.
Got it. Okay.
Well, I think it's because the azimuth pixel size is much smaller than the range pixel size.
Right.
That's a combination of things, I guess. Yeah. And
The phase
So-
is interesting.
This is not wrong then.
No.
no, it looks reasonable. So it's that orange frame there?
Yes,
Yes.
this is my area of interest. Is
Oh.
orange frame.
Yeah, this is not a PLR scene. Never mind.
My
It's not a
area.
polarimetric scene. Yeah.
Yeah, this is orange is my area of interest, and this is. I mean, I think this is the whole.
You
scene.
processed the whole frame, and this is it's a right-looking system.
Yeah.
Is that right? ALOS looks to the right,
Yep.
That's
and it's this is descending or ascending.
This is, I think it's an ascending node.
Yeah, I think it's probably ascending. Yeah.
Okay. So it's ascending
Yes.
and it's right-looking. So go back to your geographic area plot and just move the cursor where you think the spacecraft track would be relative to that orange box.
It's ascending and right looking. That means that's right. Probably be here on this side.
There you go. And it would be going upward.
Right.
Great. So what would that tell you since your time is increasing going from south to north?
Right.
And in the image processing, time is increasing going from the top to the bottom.
Okay.
What would you expect the orientation of that SLC to be? What would it look like relative to what you see geographically? Can you identify that lake feature that's in that image?
So I think this looks like a pond, a reservoir. This reservoir is right here on the boundary. This is probably this reservoir here. Looks like a water body.
Yeah, so why would it be in the middle of that frame then, if that's it?
That's, I mean, yeah,
That doesn't seem like it would be that somehow, if that's actually the frame you processed.
it's, yeah, it should highlight, right? Yeah, I did the last one. I mean, the first and the last scene. Yeah, these are just pretty much these two scenes. Yeah, first and the last.
Well, if you scroll up in this notebook, can you actually see what the numbers are that you processed?
Yes.
at least you'll get the scene ID.
These are the two scenes.
Okay, so 7806, 0660. Is that what you were highlighting on the previous geographic view?
That would be the reference acquisition, right?
Yes. Yeah, this is the 2007. This one is the reference. And
Well, that's peculiar. It should be centered around that reservoir if that actually is the reservoir.
yeah, I mean, that's one reason why I asked, does it just download this part only or the whole scene? I mean, does it just download this one?
No.
No.
It does the whole, it does the whole frame. It does
Okay.
the whole frame.
If it centers around this part, then probably that would make sense because this is pretty close to the reservoir, but yeah.
Can you go back to the vertex page, to search client page, and click on the image, the preview image below? You know, in the middle pane,
Yeah.
click on that. So maybe it's just a poorly located frame bounding box.
Also, that we're processing it maybe with some Doppler extension to the north and south.
Yeah, this looks closer to what you have, just not as squeezed.
Yes, that looks like what you.
Right. So
Not-
I think
not what you process, but what this matches the frame boundary, it seems.
Yeah.
But the processing looks quite different,
oh, okay.
in my view, because if that dark area at the top of what we're looking at now is the same as the dark area in the other image. Can you scroll? There's a scroll bar at the bottom. No, on the other side, on the other one. Scroll bar yeah, there. Can you just scroll all the way the other direction?
In the middle plane.
Yeah, that one.
Yeah, I think this is
Yeah, you
That-
can also click, if you just click on it, it sort of opens it up.
okay.
Okay, so that's it. So that seems a little odd because what you processed seems to extend twice as far north
Right.
or south. This is ascending, right? So
Towards maybe north, yeah.
But you process from raw, so whatever the SAR processor in
Oh,
ISCE
you
is
did
doing.
process from a raw. So the raw file does extend more
Oh, okay.
than the SOC. I
Okay.
wouldn't think that it extends that much more, but it does extend more.
Okay.
all right, well, let's not focus on the reservoir. Let's focus on that bright city, which is right there, and see if we can find that in what you processed.
I'd say it's there.
It's either that or the bright spot above it.
Yeah, this one, I think.
So you notice that those are above the reservoir in this image, but they were below the reservoir in the other image. Isn't that right? Or
That's
am I-
correct. That's correct. Yep. Geographically, that's correct. Yep.
Yeah, so this is ascending, right? So
Yeah.
time is, or planimetric view is flipped because time is basically flipped north to south,
Uh,
Right.
right? But the range is, you're looking to the east from a track that's to the west of the scene.
right.
So as range increases, position towards the east also increases. So the range is not flipped in this case.
Okay.
So the shape of that reservoir, that sort of zigzaggy shape, should be reversed north-south, but should be preserved east-west. So if you go back to the geographic, let's see if that's the case. Seems to be the case. Yeah, that little extension going down south
Right.
matches, I think, if I'm not mistaken.
Okay.
So So that's the case for the ascending looking right, and then descending looking right would be different.
Okay, descending looking right would be flipped both ways. This back as well, top to bottom as well on the.
Well, let's think about that. So you're descending, right? So time is increasing as you're going from north to south,
Right.
and the processing goes from earlier time to later time. So would it be flipped vertically or not if you're descending?
From what you're saying, I don't think so. It should be flipped vertically.
Right, but east-west, it would be flipped because you're looking the other direction range.
Okay, that makes sense.
So for tops, you'll have things flipped east-west or north-south, depending on whether you're looking right or left at these things.
Okay, okay. Now it makes.
Not just tops, but for any sensor.
When ISAR gets launched and it's left looking, then all of these intuitions that have built up over decades will go away because that'll be left looking.
Can you go back to the search and click on that scene one more time on the bottom and expand it? And you see on the bottom there are a bunch of other ones. Can you pick one of the ones that looks really fuzzy and hazy?
Okay.
Like, oh, maybe it's just a preview. And maybe the December 25, 2009, can you pick that one? Yeah, okay, they all focused well. I don't know why the preview looks so bad.
I don't know what those are. Are those ScanSAR images?
No, this should be, yeah, this is actually a scan. Oh yeah, it is a ScanSAR image. That's maybe why it looks so bad in the preview.
Yeah.
Right. I was about to say, because sometimes you get images that look really hazy in ALOS in some places, because in some places ALOS is very heavily affected by radio frequency interference, so ground-based transmissions of L-band radar signals.
Yeah.
And if you find one of those in the archive that looks really terrible, that'd be fun to process with ICE and see how ICE is doing.
Yeah.
The process of ALOS didn't have a great deal of protection against radio frequency interference.
Mm-hmm. All right. Well, that was instructive, I thought.
Thank you. Now I have a better sense of why my image was looking at that. Thank you, Paul. That was a great explanation. Thank you.
Well, you can thank Alex. She's the one who brought it to our attention. So, but yeah, I don't know why the framing is so off, though. That's an interesting issue.
Yeah, it's a 1.0 versus 1.1 definition.
Okay. Let's see, Deha is now on. So maybe, oh, it wasn't Deha, it was Jay Kim. Is he on?
He's also on, I think.
Okay. So maybe we can go back to that question about vectors. Jay, did you have want to go back to your question about?
Yes, thank you.
Yeah. So share your screen and explain the problem again.
Okay. Yeah, I went through the preparing for modeling notebooks, and at the end I got this Ford model result, which is a bit weird in terms of sign. So I went back to this notebook, process quad tree output, and then I get rid of these minus signs for the horizontal components. And then I got new result, and it seems it's working, but Paul suggested I shouldn't do that. And I need to figure out then what's the right solution and what caused this problem. And this signal is witchcraft coseismic from descending Sentinel-1 data.
Yeah. Okay. You can't just change one. You can't just reverse one horizontal component because it doesn't fit.
That's what I said.
Yeah.
So in your quad tree, let's look at your. So you're using descending data.
Yes.
And you're using an ICE interferogram.
Yes.
So it should be reading the ICE convention. Oh, there are two things. Like what order? I guess I should ask you what order you processed your two data. Is the reference image the first image? Because if it isn't, then the whole sign convention is reversed.
What do you mean by that?
You processed an interferogram. You used two SLC images. It
Right.
matters which order you process them in, and then which one you assign to be the reference and which one you assign to be the secondary.
I see. I use 2019 July 4th as my reference, and my secondary is July 17th, like that. So it's in time order.
Okay, so your interferogram should be in range change if that's correct.
So Gareth, I was thinking there's a step prior to this where he defines the geometry that perhaps was done for ascending rather than descending. Is that true?
No, what happens here is that Pyroco reads the LOS file from
from the data itself.
From the data,
process.
yeah. So it should do everything associated with the getting the azimuth and incidence information correctly.
Interesting. Okay. Well, then I'm stumped.
Well, we should look at the file, right, that you're modeling, maybe.
Yeah.
Like that you at the bottom of that particular notebook, there is the process quad tree output one. You actually show the file that you're modeling. Did you give it a better name than Blazik? Because that is the other earthquake.
Oh, which file should I take a look?
Go to the process quad tree output notebook. Middle one. Yeah, and scroll to the bottom. Right, so this is your pointing vector for what you have done to your solution. And it shows that your pointing vectors are positive in the x direction, negative in the north direction, and negative in the vertical direction. And that is not the pointing vector for your data.
Yeah, so I think this is with your modified code, right?
Right. So what your modified code is showing is wrong, basically, for the data you're processing.
So this part is not right.
Yeah, so this, you have to probably remove this.
I didn't do anything in terms of sign. As you pointed out, I just read the processed file.
But you just commented out the ones with the correct sign conventions.
Right. But if I use these two lines instead of that modified one, I get this.
It's quite possible you did something else wrong in your modeling.
Yeah.
It doesn't have to be the data's fault. Like is the rake correct? For example, are you 180 degrees out on rake? That would reverse the entire sense of motion on your fault.
So any suggestions that I can try? Should I run top set?
No. In your modeling, it's quite possible that you're using the wrong rake for your fault.
Oh, rake. Okay.
The rake that you're using it could be 180 degrees wrong. Because if
I thought it's near 1. I thought that's right. That's wrong. It's
I think it's left lateral. the major earthquake is the left lateral fault, and the smaller one's right lateral, I think. It's actually, I should know because I actually went there.
The main shock magnitude 7.1 is right lateral, and my time frame is between July 4th and July 17th. So I think it should be right lateral.
I would check that again just to make sure.
But I'll play with it and get back to you later if possible.
And also make sure that you define the primary and secondary order correctly in the interferogram calculation. That could be the other reason why you get reversed signs.
Yeah, thank you for the suggestion. I'll check up these two. And
Well,
can I,
if you think it's right lateral, you've got a left lateral strike rake there. So
because I'm writing a paper about Ridgecrest earthquake, so I think I don't know if it's left to lateral. I'm kind of in trouble.
we'll figure it out, but double check all your numbers first.
Okay. And strike is also from the north, right?
Yeah, it shouldn't matter for a vertical fault.
I guess other people
It'll
may
be
have.
symmetric, rotationally symmetric.
Okay. Can I come back later, maybe this afternoon for the
Sure,
office
I'll be
hour?
there. I'll be on office hours this afternoon.
Thank you very much.
Okay, that's 15 chats. What's going on in the chat?
Is it expected that the topo step would take more than an hour? Well, of all the processes, that is the longest one. And if you're running a full frame, maybe. It does a lot of read-write from the disk. So if your disk is slow, and I couldn't tell you whether the disk is fast here, but I suspect it isn't, then it will take a while. And if someone else is running something at the same time because you're sharing a machine, that could be the reason why it takes a long time. Yes, but typically when running topo, find something else to do for a while.
6 hours. Wow. That sounds very long.
But not implausible.
How many cores are on these machines, Franz?
16 or 8 cores and 16 threads, I think.
Yeah, it shows you when you log in, it tells you.
It could be about the speed of the disk rather than the number of cores.
I'm wondering if it, and does the processing default to using the maximum number, or is there a set number?
Oh, it doesn't. It uses the maximum.
Does it depend on how many looks you take for the topo step?
No.
Did it succeed though? I mean, did it finish or is it still hung? Because it may just have broken for some reason.
Sounds like it finished.
I can say that on my own machine, I do all this on a solid state drive, and it is much faster than the speed that you're seeing on OSL.
I see.
Yeah, so the topo step does take a while, but 6 hours is unusual.
Yeah. All right. Any other questions? Well, we're in a little bit of a lull and people are thinking of other questions. I'll just say, and we'll probably say again, for the homeworks, people are starting to submit them and our TAs are looking at them. There's a spreadsheet that keeps track of everything and they're putting an X if you submitted it, and then they'll be checking them. We will, we're trying out a grading system, which is relatively rudimentary. We'll put the grades in a separate place so that you don't all have to see how you're all doing relative to each other. And we're hoping if you can get them in as soon as possible, that would be great. But I think by the end of next week, at the latest, Friday next week, that's probably the cutoff for us to be able to actually look at them. So this weekend would be even better. When do the OSL instances disappear, Franz? 2 weeks or 1 week?
They will be alive for an additional week after the training.
Okay, so if you don't do it by next Friday, then you won't probably have the opportunity to do it. Anyway.
Paul, I have a question about the the homeworks. I ran a couple and did it successfully, but they were just extremely low coherence pairs and nothing really came out of it, but the code ran. Are you looking for that? Or are you looking for ones that have actual data? Because now I'm seeing that like they, in one of the homeworks, use the TOPS app to create InSAR data to then go into the model. So I'm like, oh, I think I have to redo this now because this data I made, it code work, but it's sort of unusable of the quality of it.
Right. So my feeling, it's hard to say. I don't want you to create extra work as long as you're learning. So the fact that you had a low coherence pair is okay with me, as long as you went through and you can show through the various plots that it's truly low coherence and it wasn't some cockpit error on your part that you just didn't do it right. So that would be fine. For the modeling part, I guess we provide data sets that work for modeling. And if you just want to use those or tweak some parameters relative to those, that would be fine.
Sounds good.
Yeah.
Always these snow people with the low coherence interferograms.
That was it right there. So
Well, it is Sentinel.
Yeah, it is Sentinel. ISCE would be fantastic. This coherence is going to be one everywhere.
Yeah, if you take one look, it'll be one everywhere.
Even over the ocean.
Yeah, exactly. Everybody now should get that joke now that you've gone through this training.
And then Paul too, I asked this in the chat, but I just had a question about looking right versus looking left and why certain satellites are looking that way, and how NISAR was going to be, what did Gareth say? It's going to be opposite of what Sentinel is. So sort of why did you guys do that? Or what is the benefits of having it look a certain direction?
Yeah, good question. So
Because you don't like Antarctica.
yeah, so almost all of the satellites that exist now have a focus on the Arctic. And so they want to look to the right so that they can see the Arctic almost completely. And that was kind of the case for NISAR in its early days. And we had this great idea to be able to flip both right and left. And for a certain number of months out of the year, we'd look to the right. And then for 3 months out of the year, we'd look to the left because we were hoping to get better Antarctic coverage than most other sensors provide. There are, of course, SAR images of Antarctica, but they're usually done in a campaign kind of mode. And so the coverage is not so continuous. We were hoping for at least several months of continuous coverage. After a lot of discussions and complaints about from one community versus another, we ended up picking just one direction. could have been right and focusing on the pole, but our Antarctic scientists made a strong argument that looking towards Antarctica would be even more unique than what the other missions provided, because these other missions don't focus on Antarctica. Plus, in between the time we first proposed ISAR and the time that we started developing the observation strategy, Sentinel launched and was making a lot of very comprehensive and free and open coverages of the North in pretty much exactly the same mode that we were planning to observe over the sea ice, and with the same frequency, and with pretty much a commitment to do that in perpetuity. So it seemed like repeating that coverage for ISAR was less scientifically valuable than doing the similar kinds of coverage over the Antarctic ice sheets. The prime reason for picking one direction versus two was by the time series community, mostly solid Earth. They wanted a consistent set of observations continuously so that they didn't have to combine disparate time series with a big gap in one particular look direction over the year. Does that make sense?
Yeah, that's awesome. Thank you.
And as Gareth pointed out, having one left and one right is really quite nice for where Sentinel does provide good quality coherence measurements, and ISAR is there providing better coherence measurements. You get these two vectors sort of for free. They're both free and open data sets.
Yeah, the specific advantage is, if you remember looking at the line of sight vector components, both ascending and descending right looking have a positive Y component in their line of sight vectors. With left looking, you'll get a negative north component contribution, which means if you compare the two, you might actually be able to separate out that north component.
Yeah.
Which is really, it's going to be really fantastic. We'll be able to characterize deformation in 3 dimensions, like everywhere on Earth, apart from the Arctic. And yeah, apart from the poles, I guess.
Yeah.
Great.
Yeah, so there's a comment, we will see the South Pole, will see the South Pole. Yes and no. Right now, ISAR has one limitation, shall we say, relative to other electronically scanned antennas, and that is that we have a particular beam extent. It's basically the same 240 kilometers effectively that Sentinel has, using this technique called SweepSAR. But because we use this large reflector to get that wide swath, it is our look angles are completely geometrically determined, and in order to see farther out, we actually have to rotate the spacecraft as opposed to doing something electronic the way Sentinel does. So if you just look at the geometries that we have, the inclination of the orbit, which is around 8 or 9 degrees off of a 90-degree inclination, and our beam widths and everything, there is still a small hole in Antarctica in our nominal configuration. It's like a degree or two of latitude. It's not moving that fast for most of that area, and probably you can just interpolate across it effectively. Our Antarctic scientists are not pleased with that answer, and they would very much like us to roll the spacecraft at least some of the time and fill in that hole. We've done the analysis, and we believe that the spacecraft can do it. The radar performance will be okay. It's just a matter of mission planning and figuring out which orbits we can give up in the nominal mode specifically to fill in that hole. It won't be done as regularly if we do it as we're doing the other mapping, but we should be able to fill it in. I think the scientists will be happy.
Could I make a suggestion, Paul?
Sure.
If we have some time tomorrow in this slot, could you give like the 5-minute, this is how ISCE works talk?
Yeah, so tomorrow is the day when I have this big review. I have a half an hour at the beginning of this 10 o'clock slot when I could do it. Yes, I'll do that, no problem.
Because it's kind of cool, and everyone should know enough now to get more from it.
Sure, okay. And if there are more questions, Franz is on the science team, so he knows a lot now.
And you'll see it's the same goal as TOPS, just different issues.
Right.
And with a big dish, which is kind of cool. I want to know how that's not going to get hit by micrometeorites.
Well,
Or bits of space debris.
it will, but it's probably, the dish itself is more benign from micrometeorites than electronics would be, because if it hits the dish, it goes through, and the mesh is designed so that it doesn't self-heal, but it doesn't propagate. So you'll get a little hole in it, and that should be it.
Maybe we show the video. It would be like the short sort of unfolding video.
Yeah, I can do that. See if I can find it. We've got a few minutes here. We actually
How did you
have,
call it short?
it's only
Is
2
it?
minutes.
Yeah, there's a short version.
Yeah.
Oh, good.
It's we have 3 minutes. We should take a break in a second, but I should be able to find it and show it in a few minutes.
Yeah, well, Paul, pulls this up. SweepSAR and TOPS, are really revolutionary modes in the sense that before you couldn't really do decent resolution over very wide swaths. So, before SweepSAR, before TOPS, you had only options like ScanSAR and Spotlight and StripMap, and those were not necessarily compatible with each other. And you either had wide swath and terrible resolution, or you had a tiny swath and good resolution. And the goal of both TOPS and SweepSAR is to make it possible to do high resolution and a wide swath at the same time. Pretty nice.
All right, I don't know how this will play for you, but let's give it a shot. Oh, this isn't the latest one. That's okay. It's good enough.
I know why you're saying that. This thing is the dish.
One hinge per day. The dish is 12 meters in diameter. Pretty big. That's the short version.
10 stressful days, you get that right.
What's that?
Somebody posted here, Rodrigo posted 10 stressful days.
Yeah, yeah, that's for sure. Yeah. Yeah, so I'll go into it a little bit more tomorrow at the beginning of this section. Okay, so I think it's time for a 10-minute break. We'll be back at 11, and David is on. I heard his voice, so should be ready to go, right? See you in 10.
Yeah, and in these 10 minutes, you can start up your OpenSAR lab instances.
Yeah, and if they're up, then stop them and start them again.
Oh,
But we have a theoretical lecture first. For now.
No, I know, but we might forget to remind people later, and Brian Real stuff is new.
Oh yeah, okay, that sounds good.
Yeah. All right, David, whenever you're ready.
Sounds good. So I think you should be seeing my screen. Let me modify this Zoom window. Otherwise, I think it's overlapping. You might not see me. So yeah, is everything well?
Yep, looks good.
Okay, perfect. So I don't have any eyes on the chat, but if anybody else could keep an eye on that, and if there is a question, feel free to just interrupt me and ask it, and I will do to my best of my ability to answer it. So this is a talk which was given by Piyush Agram in the last 2 years. He's now at Descartes Lab, and he kindly shared all his presentation material with me. So I definitely want to thank Piyush for doing the hard work in putting this presentation together. And he has been looking at material from various people, JPL, Caltech, Stanford, as well as the community. So definitely we want to acknowledge everybody which has an image, and we have been adding all the citations to it. So so first of all, is this, are you being, do you see some arsed out area or not?
Oh, that's fine.
Okay. So we will cover the motivation for the time series processing, and really go over the history and the different methods which exist, including the persistent scatter techniques, the small baseline methods, and more recently the covariance-based techniques. So first of all, let's look at what an interferogram is comprised of. This was also covered already by Paul in the theory lessons. So generally you have ground displacements for deformation. You would also have atmospheric pad delays from the troposphere, the ionosphere, DM errors, potential errors in the orbits, as well as noise to the data. So all of those signals are superimposed in an interferogram, and they have a different magnitudes. And here you can see in this table output from the ISCE performance model. So this is for an L-band sensor, and if we're looking at 2 points at about 50 kilometers apart, then we see about 40 millimeters or 4 centimeters of tropospheric noise in a region like India, and about 2 centimeters in Barstow in California. Keep in mind that these regions are quite different. California pretty dry. It's also an arid location. Then if you look at the ionosphere, that is a small magnitude here, about 0.5 millimeter. The assumption in this was also that ionospheric corrections have already been performed using split spectrum processing. We should keep in mind that ionosphere can be also of large magnitudes, especially on the absolute delays. In terms of the relative delays are smaller, but can still vary depending where you are on Earth. So if you go to the polar regions, generally you would have more ionospheric delay. If you think about the solar cycle, you can also see larger delays during the solar maximum versus the solar minimum. Other components which you have would be DM error, baseline error, decorrelation, etc. So if you look at the total error budget, you can still see here that troposphere is kind of the dominated factor in it. So in terms of decorrelation, partly already covered before in the theory lessons as well. So let's look at the top right image that shows you the images which with the, let's say, the pixel fraction or the coverage of the image which has coherence larger than 0.4 as a function of the perpendicular baseline. So you can see that for longer baselines, the amount of pixels which still have good coherence has decreased quite a lot. And this is for ERS and NVSAT. The baseline at which the image would be fully decorrelated is called the critical baseline, and is at about 1.1 kilometer, I think, if I'm not mistaken. So you can see now on the two images on the left-hand side, those are interferograms where the temporal baseline is the same, but the perpendicular baseline is different. And it's kind of another way of looking at the same plot. So you can see that for a small perpendicular baseline, you generally maintain good spatial coverage. But then for the longer perpendicular baseline, you can see that there are regions which are starting to decorrelate in that scene. A similar behavior you can observe for the temporal decorrelation, that is the bottom right plot. Here again, we're looking at the fraction of coherence larger than 0.4 and how that evolves over time. And you can see the longer the interferogram temporal baseline, the more decorrelation you generally observe. So by definition, extending that to, let's say, deformation signals which you want to observe, if you have a very slow moving deformation area, let's think about interseismic motion, the San Andreas is moving at a few millimeters per year. So you need to have a very long temporal baseline in order to see a significant signal. So generally, the atmosphere is pretty big, so you can see that would be problematic. In addition, knowing that you would have the temporal decorrelation, you would start to lose the spatial coverage which you normally have if you would be looking at shorter pairs. So one of the things to overcome that problem is to look at shorter temporal interferograms, but do it in such a way that you can still connect up the time series, or you can recover the displacement history. And that is illustrated in this figure here at the bottom, where you can see this overlap between the different images or interferograms. Let me also turn on my video. I noticed I didn't do that, sorry. So the other component is if you're looking at a single interferogram and you're trying to estimate a rate. So that's illustrated here by the top right dot, where the error bar gives you kind of the atmospheric variability. You can always, the temporal baseline, which was used for making that interferogram. So you could just ratio the cumulative by that temporal baseline to kind of get a rate. That will have a larger uncertainty if you only have a single image versus if you would be able to recover a whole time series of many individual epochs. In effect, the atmospheric noise through a time series analysis can be hammered down by the square root of the number of independent images or observations. Other approaches, what you could do to kind of hammer down this uncertainty is do an atmospheric correction and then go into your time series analysis, or apply spatial temporal filtering. I think this was probably covered in the lecture from Harish on ionosphere and troposphere a little bit. A key limitation when we're talking about the time series analysis, or generally InSAR, is the unwrapping problem. It's not a trivial solution, and the paper assignment already kind of illustrated that different people might come up with different answers to what an unwrapping solution might be. So there is a benefit here, and this is work done by Yunjin and Harish, and it's published in their 2019 paper, is to look at the triplets or phase closure. So the baseline plot, which is shown here on the top left corner, you can see 3 interferometric pairs. And if you're doing the closure, which means you would combine AB, BC, and you would subtract off AC, or you would add it back to CA, then you should be able to get to 0 phase in let's say a full resolution assumption where there is no manipulation to the data. Knowing that we have done some multi-looking, some averaging, some filtering, then it might not exactly close to 0, but it should be pretty close to that 0 value. If that is not the case, and it's a multiple of 2 pi, then generally you would have phase jumps and thus phase unwrapping errors. So the work here done by Yunjin was really, let's look at the bottom plot here, where you can see input percentage, and on the y-axis output percentage. He was looking at how much of the image, the fraction of the image which was incorrectly unwrapped as input, and how much using this, let's say, redundant analysis he could correct for and have the output percentage of unwrapping errors on the y-axis. So really, if you only have a few connections, let's say 3, that's the minimum to form a triplet, you can, that's illustrated in blue, you can correct in part for the error. So let's look at, for example, 60% incorrectly unwrapped to start off with. Was able to bring it down to 50% incorrect unwrapped. Now, the more redundancy you add, the more leverage you have to look for this type of errors, and allows you to do better corrections. So if you have 10 redundant corrections and the input image was 60% incorrectly unwrapped, he was able to bring that down to about 20% after doing these checks and these corrections. I don't know if Yunjin is on the line, but if he is and he wants to elaborate, then feel free to do so.
Sure. So here you can also see the impact on the right. On the right, on the top, the A subplot is an example of the closure phase. That is literally 3 interferograms AB, BC, and AC added together using the formula on the top left. So that's why you see that literally this closure phase is not perfect 0. But pay attention to the color bar here. This is really small. So you can actually, the majority of them are actually very close to 0, which is why they're not, is another different story on the phase bias that people are talking about these days. It's still an active area of research. But if you check, if we check the bigger parts on those 2 islands, on the 2 sides of this main big island, you can see that both of them, they're actually very big. They have a value actually of 1 and -1, I believe, of 2 pi, -2 pi and 1, 2 pi. And you can see all this actually in the histogram here pretty well. On the B, subplot B is literally the histogram of A. And you can see that actually there's a lot of peaks on the multiple integer numbers of 2 pi. And those peaks that are not in a 0 are the unwrapping errors. And we can see that also very clearly on the bottom in C. C is literally B, but removed the non-integer part. So that you can see basically all the spikes that is falling non-zero, 1, 2, 3, or -1, 2, 3 are from unwrapping errors. So basically with one triplet, we can see the integer part of the closure phase that is caused by unwrapping errors. And we can see that, and we can apply the same analysis to the entire stack. Let's say here in this one, actually I used around 500 interferograms, which can form around 900 interferogram triplets. And if we just check the integer number of all those 900 triplets, and we can sum them up together into subplot D. And that's why you can see in D here that the big island is very dark, almost 0, while the 2 islands on the 2 sides are actually non-zero. And you can see that also very clearly in the subplot E, where the Isabella Island is the peak on the 0, which means that the majority of the island, the majority pixel on that island has 0 non-zero integer ambiguity of the closure phase. I know it's a long term. Say that 3 times. Non-zero integer ambiguity of the closure phase. That's the unwrapping errors. And we can see that we see 2 more peaks on Fernandina volcano, which is on the left, and the San Diego Island, which is on the right. Of course, if we ignore the lower part, those lower big part are, those lower part are just random things, because pay attention to the y-axis. This is in log scale. So actually, or this non-peak spot are actually very small compared with. We will demonstrate this in the tomorrow's real data also.
Thank you, Yunjin. The other component which we saw in the error bridges were DM errors. This is a figure for on the left-hand side is the phase as function of perpendicular baseline, and on the right-hand side it's actually the perpendicular baseline plot as function of time. So the formula shown before, how baseline ends up to be a DM error, is shown on the left-hand side. You can really see it is just a function of baseline over the sine of the angle. The main problem with this is if you look at the image on the right-hand side, if you have a gradual variation of the baseline in time, it will look very much like a deformation signal. So the challenge here is really how do you correct for that? And in part, you can simply use a correlation with the baseline. So that is generally what is done in the time series approaches. So why do we want to do time series analysis? So first of all, for a lot of our subsequent analysis, either for science or for applications, we like to look at the whole displacement time series and know what is happening over time. Not all processes are linear. You can really start to try and dissect the different spatial temporal contributions to the displacement signals from various processes, be it, for example, for earthquakes, you can think about interseismic or a coseismic, a post-seismic, etc. So all these different components can really be looked at from a time series approach. In addition, there are challenges like what we discussed, one related to the atmosphere or slow-moving displacement processes, which are hidden within the noise of the data. You can really use the time series approach to address some of these. In addition, like Yunjin showed, the unwrapping errors you can identify and try to correct for them, as well as estimate the DM errors, because it correlates with baseline, and we have the baseline as function of time as well. So there are three main techniques: persistent scatterer, short baseline, and covariance-based approaches. The persistent scatterer is a full resolution approach, generally gets applied for looking at critical infrastructure, for example, like buildings, bridges, levees, but also for looking at high resolution processes or those at small spatial scales, such as landslides. It is a very computational intensive approach because you need to carefully align the images with respect to a reference image. So generally, it's very popular amongst the engineering community. In terms of the small baseline method, that is a multi-look approach. By multi-looking, it is by default kind of more attractive to apply over large-scale regions. So within the science community, we're looking a lot at let's say, the interseismic motion of faults, or at tectonic scale, tectonic processes, which might be at country scales, etc., or even continental scales. It's a preferred method to apply. Then lastly, the covariance-based methods. That is kind of taking the benefit of both methods. So persistent scatterer works very well for urban areas. The short baseline is generally by multi-looking, it works well for rural areas. The covariance-based approach is really taking the best of both of these. Given that it's PS, it also means that you need to have done a careful alignment of the images. So generally, it is a computational intensive as well, and it's becoming more and more popular because it's a very robust approach. So we talked about PS, so it stands actually for persistent scatterer. DS stands for distributed scatterer. So to illustrate what they are, we are looking here at a resolution cell. So the top left image, the square represents a resolution cell, and as elaborated before by Paul in the theory class, there's multiple scatters which you have in a resolution cell, and they all contribute, they coherently sum up the phase, at least to what the phase is for that cell, and also they contribute to the overall reflectance of this resolution cell. So if you have a set of distributed scatterers, that's shown here on the left-hand side, they look pretty similar in terms of their behavior. If you would have a single or a very dominant scatter, let's call it single point, because that's kind of an ideal scenario. It doesn't really occur in real life. You would have a single scatterer, which is a predominantly contributor to that resolution cell. Now, the phase or the phase characteristics will not change very much over time. If you look at the dominant scatter, which is a combination of both of them, that's a very likely scenario to occur. Think about you have some vegetation or low vegetation, and you have a significant outcrop or a rock or a corner reflector. That would be kind of an example for this. There you can see that the dominant scatterer would add some sort of stability on the phase behavior. So the image beneath it, that's really, let's assume that you take these distributed scatterers and you let them move around a little bit within the resolution cell. How does the phase behavior look like over time in terms of its characteristics? And what you can see is that for the single point scatterer, it's very, very flat. For the distributed scatterer, it's quite noisy, and for the dominant scatterer, it's in between. So really, for a persistent scatter approach or a PS point, we're looking to find these type of dominant scatterers by doing a statistical analysis, often of the amplitude of the images, or by looking at the phase characteristics of those images over time. So that's illustrated here by those the figure, the bottom right figure. So you can see this stack of different images, and we look at the phase characteristics, or let's say the amplitude in this case, and you can see that this red pixel doesn't really change over time. So it's considered a dominant pixel, but there are some other pixels here, like the black one, which changes to green to red, so it's variable. So that would not be selected as a PS. So by doing that analysis, you can come up with the one on the right-hand side, where the colored pixels are now the ones which are considered dominant scatterers, and the green ones are considered distributed scatterers. So the PS interferogram network generally looks like a spider network. So it has it's a single reference network. The reason for doing this is that the point scatterers do not decorrelate with baseline. The reason why we would take the center of that network generally has to do with the ease of unwrapping. So once you have done your persistent scatterer selection, you would still need to unwrap the data. And as we discussed before, the longer the temporal and the perpendicular baseline, the more challenging it might be to unwrap the data. So technically speaking, if you would make multiple pairs in here, it would have the same information in that network. So as I said before, PS points can be identified either through amplitude or through the phase characteristic. The amplitude approach was developed by Ferretti, was really the first approach for the PS, and it's looking at amplitude dispersion. Really, you have your stack of SLC data, and you can look at the amplitude for a given pixel over time. And if you take the standard deviation of that pixel ratioed by the mean of the amplitude, then if you have a dominant scatter, you would not expect much variation. Hence, the amplitude dispersion would be a small. The equation here is provided for a single scatterer. There's also variations here for multiple scatterers which exist in the community, so multiple dominant scatterers. The key thing is that the one represents the dominant scatterer, and the other scattering contributions are assumed to be Gaussian within that resolution cell. So I think if you go and Google this amplitude dispersion, you will find many different variations to this, reconfirming this plot from Ferretti. Another approach is the phase-based approach. That was developed by Andy Hooper, and it's called the Stanford Method for Persistent Scatterer. Here, what we're actually doing is we have again the same equation which we had before about that the interferogram is a combination of various superimposed signals, deformation, the atmosphere, the orbit, as well as the baseline correlated error or the topocorrelated errors. The approach here is really isolating and removing these individual components by doing spatial temporal filtering. So the assumption is that the deformation process is slowly varying in time and is spatially correlated. Atmosphere and precise orbits are assumed to be spatially correlated and temporally uncorrelated. And then the baseline error, as I said before, that can really be modeled and estimated as it correlates with perpendicular baseline. So the STAMPS approach is an iterative approach where these components are removed, and then it's looking at the statistical analysis of what is left and do the PS selection based on stability of the phase. So generally the STAMPS approach works better in the natural terrain than the amplitude approach. The amplitude approach works very well in the urban setting in cities, etc. So as I said before, once you have done your pixel selection, you still need to go ahead and do the unwrapping. There are two approaches which exist, which are frequently applied. One of them would be first to unwrap everything in space and then do the corrections in time. Unwrapping area corrections. The other approach, which is the time first, is working on phase gradients. So that can be illustrated here by the figure on the top left. So you would have the phase gradient between A and B, and you would be unwrapping that in time first. You would do the same for A and C as well as C and B. So by doing that first in time, and then subsequent you would make adjustments in space, this approach allows you to scale more easily over large terrain, over data sets with a lot of pixels. So that's kind of a frequently applied method. Then if we go and look at some of the examples from both the TRE group as well as Andy Hooper, these were very exciting results. You can see here the San Francisco Bay Area where a time series analysis has been done, and what is being plotted here is the rate for a descending geometry from ERS and an ascending geometry from RadarSat. So hence you can see different sensitivities because you're predominantly sensitive to motion in the line of sight. That really started to reveal these different fault structures of the San Andreas, as well as its neighboring faults. The image on the right-hand side is the work by Andy Hooper. It really shows you the Galapagos, the Alcedo volcano, which is inflating, and I think there was also a part of the time series where it was deflating, but this is only one component. But really what you see in the time series from Ferretti is that if you would plot a linear rate through this volcano time series, then you could also come up with something like this. What is interesting about doing a time series analysis is that not all processes are stable. There might be temporal variations to it. So it is instructive to look at the individual epochs and see them evolve over time and look at the nonlinear processes. I see there are some things in the chat. Are there any questions so far?
It wasn't a question. It was me boasting that I made the Bay Area figure.
Oh, nice. So Garrett did that. Very nice. There are effects in terms of the resolution with respect to persistent scatterers. Let's go back to the idea of the resolution cell. As I said, all the scatterers within the resolution cell contribute to whatever you see. So if you have a large cell, then the chance that you have mixing within that cell is very likely. If you have a small resolution cell, so a high resolution sensor, it is more likely that you do not have that mixing. Hence, generally, you would have a higher density of PS points, and that's illustrated here on these results here for RadarSat as well as TerraSIR-X, and you can clearly see the impact of the PS density. Another example where these approaches gets applied is for building monitoring. I like this plot because you can see the temperature on there as well. And there are other results in the community, for example, for monitoring bridges, especially bridges made out of steel, etc., where you can actually use PS to look at the cables and look at the structure of it, but where there is a significant impact on the temperature. So you can see that over time, if you would plot the temperature time series with respect to the displacement time series, that there is a correlation between them. And especially, for example, for some of these buildings as well, you can see that as a function of height, because there is a temperature gradient within the lower part of the atmosphere as well, or at least within the building infrastructure. So that's a pretty cool application for that. So summarizing up, for PS, really it is a full resolution method. Because it's full resolution, it needs to be very carefully aligned and depends thus on co-registration. The historic sensors, and also till a few years ago, we were predominantly using software packages where we would do a polynomial co-registration to do that. And for the historic sensors, that might not always be as trivial to go ahead and do that, especially when you have large baseline, steep terrain, where the orbit vectors might not be as well constrained. This is pretty challenging to do. So I think historically PS techniques were definitely more popular against the engineering group, but with the current fleet of sensors where you can do co-registration almost only based on the orbits, for example, for Sentinel, some of these challenges are going away. So perhaps one thing which we generally observe is that PS is a full resolution method, often too high resolution for some of the tectonic applications in terms of how do I go and model it. With tectonics, you might be modeling processes at depth, so you don't need to have the every other pixel or every pixel type of resolution, mainly because the inversion models can't handle it. So downsampling is an often applied method. So here is the downsampling done by Rowena Lohman. So it's a paper we're looking at quatrain and various downsampling methods. So PS is applied in the tectonics community generally when the other methods fail, which we will talk of in a little bit, and then downsampling would be applied. So the next method is the short baseline subset method that was developed by Bernardino, the Napoli group in Italy. Here you are really looking at limiting or doing a dynamic triangulation of the network and limiting the spatial temporal baselines. Often there might be some sort of constraint which you can think of, the maximum decorrelation that you would allow, and you would assume something for the temporal decorrelation as well as the perpendicular decorrelation. And you would just build your network, and that's the network which you're working off. As you can see, much more redundancy, and the idea here is really that you have these qualitative short baseline interferograms which are easier to unwrap, and with the redundancy you can definitely recover it, the displacement history. So you have this network, you would try to recover, or you would recover the displacement history by doing a least squares approach, and you would invert it with respect to a certain reference epoch, and everything would be relative with respect to that epoch in terms of displacement. So in this case, it's at T0, which is assumed as the reference time, and you can see that as of course and zero displacement, and everything would be moving relative to that time. And then you would also fix that in space. There would be a certain reference location. So like I said, the original approach was done by Bernardino et al. It actually started off from the original full resolution co-registration method. So it was time evolving, but then over time there were modifications where with additional multi-looking and the filtering, there was actually no longer a need to do the co-registration with such a careful as a careful approach. So generally, what you can see is that the SBAS methods are pair by pair InSAR processed products. They're multi-looked, they're heavily filtered, they're geocoded, and the analysis is done in the geocoded domain. So the community really focused mainly at the inversion strategies. Broken networks, thinking about seasonal step functions, exponential decay, post-seismic, etc. There was a significant focus on that, and there's definitely quite a lot of different variations to that in the community, like the NSBAS approach, the MINS approach, etc. Still, it's very widely applied within the community for at least tectonics. So here you can see an example for caldera in Napoli, the Flegge volcano. And what you can see here is over time, you see this nice subsidence and then again an uplift process while still maintaining quite a lot of the signal in different regions. Of course, if you go to the very vegetated areas, they are definitely more challenged and you would still lose your pixels in those regions. So an L-band sensor would probably maintain a little bit better, and that's what Paul was talking about in terms of NISAR would have even better coherence preservation. So showing this image from Brian, it's often used for advertising purposes, but it kind of shows you what the strength is of a time series analysis. And he was looking here at aquifer depletion and recharge in the LA area, and I believe that this was from ERS and MVSAT data, multi-year time series. So very interesting plot. And analysis. So the last set of methods are the covariance-based methods. These really take the best of both, right? The PS and the DS. So these methods are aiming to be well suited for both rural and urban area and mixed areas. And the initial approaches were the phase linking and the SqueezeR approach. Now, how they work is they are starting off similar to the PS from the full resolution images. And that means that it is a very time-consuming approach. But what you're doing is you're identifying pixels which look alike based on their amplitude. So you would look at a pixel and look at its amplitude histogram, do the same for its neighboring pixels, and identify which of these pixels look alike. So when you do the small baseline multi-looking, you're just averaging over a whole block. But then for these covariance-based or the adaptive multi-looking approaches, you're only using these pixels which look alike when you're averaging. So that really allows you to preserve the resolution as much as you can of the PS, and then you would have the resolution for the DS, which will be changing depending on the location. So like I said, it's predominantly identified based on the histograms from amplitude, and it is a very time-consuming approach. So to kind of illustrate that, here you can see, let's say in interferogram, we're trying the pixel of interest is the center pixel here. For the small baseline processing methods, you would have averaged over the whole kernel, which looks purple, including the arsed ones. If you are doing the covariance-based approaches, you would really start looking and identifying these pixels which look alike. So let's assume that these are these arsed pixels which have a similar neighbor to the pixel of interest. So when we were doing this adaptive multi-looking, we would only be averaging over these arsed pixels for that pixel of interest. So here you can see an example processed by Harish. Yes, go ahead.
Will you go back one more time? I think you had it on the slide, sort of the definition of look-alike. How do you decide which ones look similar? You have or did you already say that and I just missed it?
Oh, so, yeah, so no, that's a good question. So you can look at a given pixel and look at its amplitude. You have a whole stack of SLC data now, so you can start building that histogram of how that amplitude of that pixel is over time. You could look at different characteristics of the histogram, the skewness, the mean of the histogram, the standard deviation of the histogram, etc., to define commonality between different neighboring pixels. So you could say the skewness needs to be the same, and the mean needs to be the same. If they're not the same based on a certain threshold, you could say they're not neighbors. For more details on exactly what is being used, I would need to refer you to some of these papers, which are added at the references here at the back. Okay, so here are some of these examples. So here you can see there is an Anderson-Darling test, which is applied to the amplitude to kind of identify a self-similarity. So this is the San Francisco Bay Area, and the zoom is has part of these the Golden Gate Park. This is vegetated, and then the other areas here are of course very densely populated with buildings. So a PS point, of course, should be a neighbor with its own, really. It's a full resolution. There's only one pixel which has that characteristics. Now, if you go for the regions which are more rural, like that park, if you go to a grassland, there would be multiple pixels within that grassland which would look alike. Here you can see that being manifested here. So these rural areas, the grasslands or the Golden Gate Park itself, you can see has many similar looking pixels, self-similar looking pixels. While if you go towards the urban areas, you can see that the self-similar pixels is much lower, and in some cases it would just be 0, which means it's a PS point. So wanted to kind of zoom in on this example. So this is the input of that product, an input SLC looking at the amplitude here. If we are now going to clean that up and let's say identify those self-neighbor pixels and average to the adaptive multi-looking, then you can really clean up that image quite a lot. So the salt and pepper noise which you saw before is removed. And you can see that the buildings generally they're not changed very much, because they would be a self-neighbor of themselves. While the vegetated areas, you have a lot of regions to average upon. So it really cleans up the image a lot. And if you start off from these cleaned up images and you would make an interferogram, the interferogram would look less noisy. It would be easier to unwrap as well. So we will talk about it in a little bit. Really, we're looking at the covariance approach, and the covariance approach really makes all possible pairs. So when we were talking about the PS approach, it was doing it with respect to a reference image and did not have any redundancy. If we're talking about the small baseline approach, it was doing a certain network using some sort of assumptions, Dylongi triangulation, for example, on which pairs to be part of that network. For the covariance approach, we're really making all possible pairs. So the covariance matrix is just a multi-looked interferogram for each pixel, and the correlation matrix is the normalized covariance matrix, and the correlation matrix is between 0 and 1. So to illustrate that, here is some examples made by Haresh over an urban area as well as an agricultural field. So you can see the magnitude goes between 0 and 1. So this is the coherence matrix. You can see the values goes from 0 to 120. That is the number of acquisitions in time here as well. It's a square matrix because it's a coherence matrix or a covariance matrix. And what you can see here is that the coherence remains pretty high over time for these urban areas. But if you look at the agricultural field, decorrelates very rapidly in time, and the coherence drops off close to zero very quickly. You see, however, these patches which appear, and that really has to do with what is happening on the agricultural field. So if everything, for example, is mowed down and you have quite bare ground and it's not touched, then you would preserve the coherence longer. But if the vegetation is growing, if somebody comes in and plows the field, or there is a significant precipitation event on that field, then generally you would observe decorrelation. One thing, if you would just have precipitation and would dry up, generally often you would see that it would have recovered as well in terms of coherence. So there's a lot of information to extract from these covariance matrices. Part of this can be built upon what is done in the polarimetric community and predominantly tomography. So one way to compress this matrix is to do a PCA approach, so principal component analysis. Now, those work well, but a more accurate version is through phase linking. So you remove all the redundancy, and that is really the basis of the covariance-based approaches these days. So you have a whole stack of SLCs as input. You would actually do this covariance approach, which is still in the complex domain. So the covariance matrix is a complex matrix. So you haven't done any unwrapping. There's no assumptions or errors which gets propagated from there. And as output, you would get a clean SLC stack. So like I showed, the figures which I showed you before, that was one of those SLCs, the before and the after. So definitely it is cleaned up, a lot of the speckle is removed, and the unwrapping should go a lot faster. So here you can see an example of that for an interferogram. On the left-hand side, this is over the Long Beach area where we see a lot of oil pumping, and on the right-hand side, it's the same one, but it's cleaned up. So that is much easier to unwrap, and that's generally some of the methods, like the time series approaches in stamps. They do a little bit of filtering prior to unwrapping to ease the unwrapping process. So the latest developments, and this is becoming more and more important with Sentinel and ISAR, and you have these long records of observations, is that you don't want to invert the whole covariance matrix over and over again for each pixel when you have 150 or 200 acquisitions. So the sequential approach, which was developed by Ansari, that is really splitting the whole stack in multiple mini stacks, and the covariance approach is done on each of these mini stacks. So really what you're doing is, let's say you have 110 images and you split them up in mini stacks or 10 or 20, then you can really compress these individual stacks to individual SLCs. And whenever you want to do the update, you only need to do that on the last mini stack. So it's much more computational efficient. It is still a lot of work which is ongoing. And I know that Haresh, Piyush, and Yunjin, and others are really working on that and to replicate that in the French framework, which is also available online. So definitely, if you want to have some try it out to see how that is going, it's still an active development area at the moment. So here you could see one of these examples done by Haresh using CSK data over San Francisco, where you can really see that the conventional approach would be very noisy, but then with this covariance-based approach, you can really clean up the image a lot. So it's pretty impressive, but again, very time-consuming. Another example here done by Haresh is for the Kurdistan earthquake. He did the whole time series analysis using the covariance-based approach, and then generated a time series and fitted the different components. So this is the co-seismic component is on the left, and on the right you can see the post-seismic component. And there is 3 points here marked A, B, and C, where B is in kind of the peak area, C is slightly out of the peak area, and A is away from the main displacement, not in the far field. But to illustrate you how the time series looks here, you can see pretty stable pre-event. Then you have the co-seismic event with a main main jump. So that was the coseismic plot which you were seeing, and then the pole seismic shows you how the decay is after the earthquake. So one thing which was kind of key from this analysis, and I don't know if Haresh is on and if he wants to elaborate on it, but the comparison with the small baseline method where you would have done multi-looking, when you do multi-looking and you really go to these very peak deforming areas, you could have aliasing and you could be underestimating the signal. So when you try to recover the displacement history, you might actually underestimate the signal for the coseismic event. I don't know, Haresh, are you on? Don't think so. Okay.
Didn't see him there.
Okay. Yeah, so this was a very interesting work. And also if you check in literature, there's more publications about this earthquake event. The other thing which you can start to look at is, again, these coherence changes over time. So this is exactly the same thing which we showed before in terms of this coherence matrix. Everything before the earthquake looks alike. The surface hasn't been changed a lot. Then you have the earthquake, and everything after the earthquake again looks the same, but anything which crosses the earthquake event is decorrelated. And at least this is for a pixel over here, or in the deforming area. If you would do it for a pixel in the far field, of course, you would not see that disturbance event. So that's another benefit of this time series analysis. You could use it for disturbance mapping. So coming to kind of the conclusion of the talk, there are still challenges for time series analysis. One of them is phase unwrapping, especially when you have these high resolution data sets over large areas. It is very computational intensive, and it's not a trivial process. The other thing is the propagation delays. So troposphere is present for all the sensors. If you go to L-band, you also have ionosphere, but if you're looking over large areas, ionosphere is also present, but definitely we can in part correct for it using the approach what ISCE is doing with 2 frequency bands, or by doing a split spectrum processing as demonstrated in the previous course. For troposphere, generally can estimate it from the data, but you're making assumptions. So that's where it's challenging. You could use auxiliary models or using the time series approach, but those reduce it. It's not yet removing it completely. So that's kind of an active research area in the community still. Mission continuity. We're looking at small magnitude signals. We like the idea of a long mission duration because it allows us to decrease the noise level and start to look at these very small deformation processes. We haven't really talked about it. I saw some comments on the Slack channel, combining different geometries. That's very powerful. And also Garrett mentioned it, and Paul from left looking and right looking geometries. How to do that at, for example, the time series level. That's also still challenging because of different sampling of the different sensors. Then computational and storage needs. I mean, we're going to, or we are already in a decade where the volume is just tremendously big. So the ability for us to update these stacks while not keeping all the data, kind of coming up with efficient methods is an ongoing topic of study and research. And lastly, uncertainty. So you can see that more and more of the InSAR community products are being used in decision making. Also in modeling is the actual propagation of uncertainties, and often that is not fully reported. So again, that's an ongoing topic or challenge for the community. So yeah, so I would leave it here and take any outstanding questions if there are any.
There are at least 3 questions in the chat.
Okay, fire away.
So the first one is NESD the best approach for co-registration?
I would defer to Haresh, but he's not here. So, and I think Yunjin is here as well. I think from my understanding, for at least for a Sentinel perspective, the geometry based co-registration should be sufficient. I think for the more challenging one for ISCE, where for L-band, where the ionosphere is more of an impact, I think the NESD type of approach, or let's say where you do it based on a network, is more important. I don't know, Yunjin, if you have any thoughts on that.
Yeah, I agree with you. Just one more comment is that when the community developed the ESD or the nested NESD, that's the time when we don't know the TOPS imaging mode geometry very well, and now we know it much better than then. And actually, by considering that geometry pretty well with the precise orbit, we now can, that's literally the geometry co-restoration is about. So that part can be taken care of pretty well. And we tested with C-band. The ionosphere is not that big. So actually, most of the time that you most likely will end up with just using geometry for co-restoration for Sentinel-1 is enough. Even though you might still see some phase discontinuities in part of your data, but if for a lot of applications, that doesn't really matter much.
Thank you.
Okay, there's a question about have you had any success using covariance methods to monitor landslides?
So I haven't applied the covariance methods myself for landslides, but if we go back to the initial methods like ISCE type of approaches have been applied for definitely for landslide mapping. Yunjin, have you applied anything for landslides using fringe or the more recent approaches?
No, I don't have experience.
There is a pretty good body of literature out there from the TRE and TRE Altamira teams using SqueezeSAR methods for landslide monitoring.
It's basically
been applied.
Yeah.
It's basically kept Alessandro Ferretti in business for for 20 years.
Yeah. So definitely, I mean, I would probably apply one of those methods for landslide mapping above the SBAS approach, just because you're looking at the highest resolution and you don't want a really big rate resolution. So adaptive multi-looking, that type of approach would be well suited for that type of field of study.
Excuse me, am I audible?
Go ahead.
For the time series data sets, like for data sets more than I think 100 scenes, has any other alternative of this covariance based method, like for the distributed targets actually? Just
Yes.
used to Ansari paper you told us, like if we group it in the small patches and make it like use it as a particular SLC data sets. Any other method like that? Like another which is less complicated during the implementation?
Not that I'm aware of. I think also the developments which are being done at JPL are building on top of that InSAR methods. Yeah, so I don't think there are currently different approaches for beyond the mini stack, which is currently being pursued. But that said, there might be papers which I'm not aware of that are exploring new methods. So definitely it's an active research topic. So somebody might be working on it at the moment and might not be aware of it.
So any other like method for like I think this covariance based method will be very much like computationally challenging for like big data set, like more than 100 or something for the distributed.
So the proposal from Ansari is to actually not need to do that each time for 100. You would only be doing it on the, for example, on the mini stack, which you're currently processing. So once you have done a mini stack, you would no longer touch it. There would be a link between the last SLC from the mini stack to the next mini stack. So that's kind of a challenge. If that is a decorrelated or a very challenging long baseline, then there might be some challenges there to recover the displacement history, I think. But the idea is that So if you have those 100 images, you would have 10 mini stacks. And once you want to add image 101, you would only be talking to the last mini stack to do the updates. So you would not really be touching all the 90 other data sets anymore.
Okay,
So there's
thank
a
you.
question about ionospheric corrections, and do they have a contribution to the phase closure problem?
So the phase closure problem is really related to unwrapping. So you would have unwrapped the data. Like we said before, there is a superposition of all these different components, and ionosphere is one of them. So ionosphere could contribute to a phase unwrapping error potentially if you have some of those streaks in the data. So it could be a cause to it, but it doesn't need to be the only one. Probably decorrelation generally is the main challenge. You also have other superimposed like troposphere, which could cause an unwrapping error. So the closure is really looking at the unwrapped and making sure that that is consistent for a triplet.
Can you throw some light on present ways of deriving multidimensional time series from different imaging geometries? It's the 3D or the 2D or 3D problem.
Yeah, I mean, so let's say I want to do a landslide and I want to study a landslide and I want to look at the downward motion, let's say downslope motion. So you would either make an assumption of decomposition, but what you really want to do is you want to be able to blend the ascending and descending time series, because it allows you to increase the temporal sampling a lot of that process. So it would be interesting to see how you can combine ascending and descending data, knowing that, first of all, they are not looking at the same time of day. Second of all, they're looking at a different geometry angle. So either you do some sort of assumption on how you are decomposing it, knowing that, for example, north-south, you're not very sensitive about. So that's, I think that personally, that's where I think it would be interesting to kind of try to blend ascending and descending data from a time series perspective. From a rate analysis, I think that is more straightforward, because you would have just estimated a rate over a certain period of time, and it becomes a simpler approach, because you don't have that much issue of the, let's say, the time of day, as well as the referencing issues.
And there's one last question, which is, does the Squeezer approach underestimate local deformation? For example, if there's just deformation on a building, by Prime's method, we are making neighboring pixels look like each other and average out the signal.
So the Squeezer approach is also doing, it's combining PS and DS. So if the pixel appears as a PS, it would have preserved the resolution. For the DS, it would have done adaptive multi-looking, looking at the similar nearest neighbors. So generally, if the nearest neighbors had a significant different displacement history, yes, then you would have smeared it out, I would say. But I think overall, the intent is to preserve resolution of that method. I don't know, Yunjin, if you have any additional thoughts on that?
No, I think you got it great.
Yeah. Okay, so how are we doing on time, Paul?
We're over time.
Okay, good. Or bad.
As we normally do. So let's take a break until, shall we say, I think you're up next again, right, David?
Correct.
So how long a break do you need?
Probably 2-3 minutes to just pull up things and be ready.
Okay. 12:10 then.
Okay, sounds good.
Be back at 12:10, 6 minutes. Thanks.
So we will be giving a brief demo, 1 hour, about area tools. There is also a homework assignment associated with this part of the class. So let me briefly share my screen. So area tools, I will give you a brief introduction about area tools and the products. So there was a project at JPL in collaboration with ASF, which was called Getting Ready for ISCE, where we developed beta products that looked like the ISCE beta product, and those are NetCDF products. We are producing quite a lot of these products and making them available to the community to kind of experiment and get familiar with how ISCE data might look like. So I briefly wanted to show there are, if you go to the lecture notes and the videos of the lectures, in past years we also had an let's say a download or how to access community-based SAR data or InSAR data, notebooks and introductions, and so I will briefly recap that, at least for this archive. So one way is to go to the Vertex page, which is the ASF DAX search engine. So you can Google that page, ASF Vertex, and when you click on the link, you will end up over here. And to find those sample data sets for ISCE, you would change this data set to S1 InSAR beta. So it's considered an InSAR beta product. You can see that it says that there are, let me see if I can remove this, that there are about 600, almost 700,000 files. So if you would go and look at the filter, you can change the file type to standard product NetCDF. That is really the product which is generated. All the other layers are on-demand layers, which gets extracted on the fly out of the product. So you can see there is about 140,000 products that are currently in the archive available. So if I did a brief search, and we will be looking over the San Francisco Bay Area today and also tomorrow for the MinPy tutorial. So if I would go and zoom in over some of these regions, I go to California's San Francisco area, and I will draw a little box. It tells me that there is 2,000 files which intersect with that location at the moment. So all these different tracks, they do exist. If you would drag up the bar, you can see here all these individual interferograms which are available on a frame by frame basis. So for our analysis, which we will do shortly, we will be looking at track 42. So that's the Sentinel track number. So I will just refine my search, which is a descending pass, and it will show me only the tiles over here. So there's 730 tiles, and if we want to look at some of them, it says the latest tile is from June 21. So there is about a 20-day lag on this archive because it's using precise orbits. So it's operationally or quasi-operational being added and has the whole Sentinel-1 record in it. So if you want to go and download it, you could click here on the download pointing arrow. You could say API URL, and here you can change the format to a build download script, which would be a Python script. You can click download. You will get the Python script to a chmod 600 to make it executable, and then run the script, or call Python and then the script name. That would allow you to download all these different products. So that was kind of in a nutshell the visual way to do it, the GUI way. So let me now go towards the area tools page and show you that as well. So area tools is a package which was developed by a few of the people which are also here on the call. including Simran, Emre, Brett, and contribution from Yunjin and others as well. So this is really a package which is meant to do manipulation of these standard products. They're NetCDF products. They have a specific formatting. So it's the cropping, the stitching of these different products, and also the preparation if you want to go into time series processing, like for example, MinPy. So it's not a time series processing package. It's a manipulation package which gets you ready to do time series. So you can see here over California, these individual tiles. The package is able to generate you a spatial, temporal, consistent stack, which directly can go into MinPy. So to do that, you need to stitch along track these different frames. And as you know, coherence is just a value between 0 and 1. So that's a simple blending. But the unwrap layer, it will have a multiple of 2pi discontinuity, which you need to minimize. And actually, it's a little bit more complex than that you would need to do. In addition, there is a specific way of formatting the baselines and the incidence angle, the heading angle, all the geometry information specifically. When we were doing it for TopSap, when we're doing it for StripMap, it was a 2-dimensional layer, so just a 2D data set of incidence angles. For ISCE, it's going to be a cube, and it's a very coarse cube where you would actually use a DM to intersect that cube to go towards the fuller resolution. So all of that is being detailedly discussed in the area extract notebook, which is the homework assignment. So anyway, there are this information on how to install it, and feel free to tag up in the Slack channel if you need help, if you want to install it yourself or locally, or if you have any questions on that. So that's the area tools package. There is also an area docs webpage. Let me see if it's down here at the bottom. Documentation, and that's where all the area notebooks are. For this class in the repository from Paul, there is only a few of the area notebooks. But if you want to have more notebooks, you have a GDAL basic notebook, how to define AOIs, to download the extraction, etc., misclosure, which we were talking about just now before in the theory, area plot and TS setup. So this is the homework assignment, the area extract. I will not cover too much about area downloads, but again, you can look at that. It gives you, let's say, a command line interface of interacting with the DAC API for downloading products rather than using the GUI. So, okay, now let's go towards the class of today. If you haven't started yet your server, please go ahead and make sure your server is started. I don't know, Paul or Franz, if this command which was posted in the Slack channel, if that needs to be ran now or if that is no longer applicable.
I think that only is needed if you're working on the terminal.
Okay, so I shared it with a couple of the colleagues. So if people need it, then they would be able to repaste that in the chat or point you towards that. So what I did is I'm working here in the top level folder. There is actually an area tools docs location as well. I just recloned it because I noticed this was not being updated. So one thing which you could do is just remove that folder and reclone it, or you could work from the location in here in the geosync. There is also an area tools folder in there. So this is area extract. Sorry,
David, that you're saying that that there have been updates to that folder in geosync, and if they had it previously, then it won't be up to date. Is that the problem?
Yeah, so I didn't know. I think it should be fine in the geosync folder, but I will show another notebook which is not in the geosync folder in addition to this. And if people would want to follow that, I will just demo it because it takes a long time to process it. So I'm not saying that it needs to be done, but if you would like to do that, then you can find those notebooks. There should be another folder which you have, which is called Area Tools Docs. That one should be cloned as well as part of the setup.
I see, it's already there. Okay.
Yeah. So I'm going to work from this notebook. If people want to reclone the notebook, again, this would be a command to reclone the notebook. And I don't know, Simran or Brett or Yuan,
Yeah, I'm here.
Yeah, so could you recopy that in the chat, perhaps?
Yeah, I'll go ahead and put that in the chat.
Okay, thank you. So let's start with the area tutorial for the plotting. So this is in preparation of if you would go into time series, you would like to know what your network looks like. So it's the area plot tutorial. So we do recommend you to use the stage data. So changes fail to true before you proceed. And the real goal of this tutorial is to look at how does the coherence change over time, how does it change in terms of the length of the perpendicular baseline and the temporal baseline. So the first cell is really just the initialization of the notebook. If you haven't done so, you should change the kernel to UNAVCO. And then you could just execute the cell, making sure that the stage data is set to true. So if you run that, it will just go and download directly from the ASF bucket and unzip the archive of the products to use. So there's only a few which we use from 2015 till the end of 2015. I think it's 1 year of data only, just to make an illustration. Really, as I said, we're using these sample products. There's different download command options. There are instructions here if you don't want to use the stage data. Again, you would need to have a netrc file. I think all of you have done that now for the previous classes. So that should work. If not, it gives you the instructions on how to do that. If you would not control, let's say, anything, you would just download all the data. It would take 20 minutes, but if you only limit it to a year, which I just did over here, it doesn't take 20 minutes. It should go relatively quickly. So I will update that in the next iteration. If you once you have downloaded it, you can look at the directory. Let me also do this here. Okay, so it's doing that now. You can see that these are the products, and you can see the Sentinel-1. So Sentinel-1 is the product, is a geocoded unwrapped product. It's for a descending pass. It's right looking. It's for track 42. That's the track which we're looking over San Francisco. It's for the top sensor. And then here it gives you the date of the reference in the secondary. And then here it gives you the UTC time, really. So it's 14:07:45. And then the last two strings here is the northernmost and the southernmost latitude of the product. So generally, you might sometimes see two products, like this one here. You would see two products which have roughly the same UTC time because they're just adjacent along track. But then the latitude really is, you can see based on these northern latitudes, you can see that they are adjacent as well. So that means that for that interferogram combination, you would need to stitch two pairs together to make it seamless over that region of interest. So that is really talking here about the different products here. So I can skip that now. If you want to get the
David. Do you think we should mention really quickly, if you're going to skip over the download, about the virtual data processing options and option to use URL links downloading?
Yeah, sure. So that's a very good point. So we have added the capability for virtual data processing. So you do not download any data. If you look at the area download and you do you run the help function for that program, you would actually see that there is an option for virtual downloads. In that case, you just get a URL of links which points to these files in the DAC location. So the subsequent processing down the line would only be accessing the data virtually using GDAL VSI and only moving the data which it needs at the very end. So we have been experimenting with that and are currently developing that under a funded project which we have access to improve our algorithms for cloud-based and alongside data processing. And we recently, Emre contributed that also to the ISCE repository. So the ISCE TOPS processing you could also do virtually. Thanks, Tim. So if you want to get an overview of this area plot, you just run it with the -H option. Let me see, is it still running? Yeah, there it is. So here you can see all the inputs, the image files, the ones which we have just downloaded. You can specify a bounding box, the mask, the number of threads, and then really the things which I will touch upon is this crop to union and the bounding box, as well as plot tracks, plot perpendicular baseline, etc. So the plot tracks really gives you the latitude bounds to see if there is any gaps along track. The perpendicular baseline plot, that's just a conventional plot which we have been seeing before in the lecture, but you can also color code that based on average coherence. So that's this option. And then lastly, there's options to compute, let's say, a 2D map on how the average coherence looks like. And you can also put it out as a raster if you want to load that in different data sets. And then there's the minimum overlap, which I will touch upon in a little bit as well. So to specify the number of products, it's just a -F option. If you use the area download, products are by default downloaded in the products folder, and you saw all this S1, etc. You can just use a wildcard. That's generally the easiest way, -F and then S1 wildcard, the netcdf extension. Then the cropping and the spatial subsetting, this is an important one. So whenever we go into time series analysis, you want to make sure that your data is geocoded, but that the bounding box which you provide to min.pi, it's really a 3D cube, where the 2D dimensions are longitude, latitude, and the 3D dimension is time. That would be, or interferograms. So the cropping, that's how you would control that spatial extent. So here's an example. Let's look at this first plot, the intersection plot, where you can see 3 black dots, and the line is really representing one interferogram product, and this is the other interferogram product. And then on the x-axis, those are the interferogram numbers. So that would just be another interferometric pair for a different time epoch. So if you do the intersection from all of them, it would look at the region which is common to both areas. So it would, by default, limit it to the red extent. So if we would do the union, it would be the most royal. It would look at the biggest extent which is possible. But if you do union, you can see that there would be no data for this interferogram here, over here, and over here. So not all time series methods can handle gaps in the time series data. So the NS-bus, that one, for example, could handle that, but a conventional approach might not. It's the assumption on the inversion going from a redundant network to a single reference network. So you could also provide a bounding box option where you say, this is the region which I want to process, or I give you a shapefile. So those are options which all exist in combination. So key thing to keep in mind, if you give bounding box option, which is very big, let's say you give the whole of California, and there's only data which you have over San Francisco, then it will make you a stack over the whole of California, and it would have filled all the rest with zeros or with no data values. And then you can still combine that in combination with one of these two on top of that. So let's assume that one of the images doesn't happen. Let's say there is one image which has just one line of data in it, and you would say intersection, then everything would just have a single line in it because they're all cropped to the common intersection. If you would have done union and a large bounding box, it would have just stitched everything, but it would have not worried really about the spatial extent. So again, this is really detailed, discussed in the area extract notebook, which is the homework assignment. How to run the actual program? Here is the qualitative plot. So we have area plot. We then do the -F option with the wildcard for the products, and we say go ahead and make the coherence plot, the colored coherence plot, and compute the average coherence. Now this takes quite some time, You can actually set the multi-core to higher. You can do, I think it's -NT number of threads. You can put that up if you want to, and that's generally the water mask, which takes a while to generate, because for the water mask, we're looking at a vector data set, which we're rasterizing, or we are looking at the national land use map from USGS, which we're using to rasterize as well. So again, you can execute it. It will take some time to run in the background. So I have already run it ahead of you. So feel free to run and execute that cell. Then if you look in the folder, once you have executed that cell and it's complete, you can see these different figures which have been made. You can see average coherence and a header file. So this is really an NV file with a header file to inform about the geospatial information. And then you have these coherence plots, the average coherence, which is a EPS plot, but it also has a corresponding PNG plot. If we would go and look at these plots, so we have an issue with re-rendering these figures, so you would need to double click on the cell and then execute it, as is shown in the figure display here. So here you can now see the baseline plot, which we talked about, and it's color-coded by coherence, a metric between 0 and 1. And generally what you would see, if you would make very long duration pairs, the coherence would go down. If you have short pairs, then you preserve coherence. As you can see, the baseline, it doesn't really matter that much for Sentinel-1. It's a very tight orbital tube, so it's only like 200 meters baseline. Similarly, we can look at the average coherence with time. So that's taking it from all the interferograms and doing this spatially. So you can kind of see the San Francisco area appearing here. So this is the water here. Here's the Golden Gate Bridge, I believe. This is again a vegetated area on the mainland, and the Bay Area is over here. So you can really start looking at these features a little bit as well. So this is instructive, and Yunjin will talk about it a little bit more in the MinPy tutorial as well. Generally, these regions of low coherence, you do not trust, they are prone to unwrapping errors. So you do want to get rid of them eventually. So you could mask them out in your time series analysis. Yunjin will talk to you about different ways to do that, and also correct for unwrapping errors. So here's another way how to open that raster in a Pythonic way. So the plot layer, that's a function which I had created, or which we have created here at the top of the notebook. So it's over here, plot layer. So it's just calling this function here. And so it's just visualizing this in a Pythonic way. You can also look at the spatial extent. So generally, that's the first thing, the plot tracks, which we look at. And it's telling you what the frames are. So wherever it was possible to stitch these two frames, it has already done it. So it just says this is the start, and that is the end latitude for that interferogram, and it's doing it for all of them. So if for some reason there is something funky that happened with the data processing, and it was just at the DAC, and you had only like a very small black, two black dots which are very close to each other, and you would have done the intersection between both, then it would have only done the bounding box area would have been between those two areas, or two black dots. So it would be very small. So this plot is very instructive in the sense that you can see if something goes wrong ahead of time, or if you want to use a minimum overlap area. So the minimum overlap area allows you to bypass that a little bit, and that's detailed in the time series setup notebook a bit better. Any questions so far? Okay, so I've done the same thing, but now I let it roam free, and I downloaded all possible data for that location. So as you saw in ASF webpage, there were about 700 products. So what I did is I set the use stage data, I set that to false over here. And then I went to go ahead and download all these products. And there is actually a multi-core option, which I've used before. But here I just showed it for one thread. So I think it's called -NT. You could do all, or you could set it to 4, and it will do things in parallel 4 times. So that can speed it up a little bit. But in effect, you can see all these products over here, and they go up till 2015. They go now up until 2021-07, so that's a few weeks ago. I just executed exactly the same cells to see what we have available. So then you can see the network over here. And I was referring in the past about these more decorrelated interferograms, which are generally the annual interferograms. So if you're making an annual interferogram from summer to summer, that might be good. If you make it from winter to winter and there's snow in winter, then generally that would not be good. If you do it from a monsoon season to a monsoon season, generally it would be decorrelated. But if you take a period which is good and coherent, and you go 1 year later, and that's again a coherent period, then that was good. Then that would also be a good interferogram. So looking kind of between these annual pairs, and you look at these short pairs, you can see that actually there seems to be some sort of seasonality in it. So it goes from this is a little bit more orangey to yellow to more orangey again to yellowish interferograms. Might be hard to see, but there seems to be some sort of seasonality as well in there, which you could expect because of summer, winter periods, or some more vegetation or wet periods, etc. And the area around San Francisco is more humid as well, so that might have some sort of impact. And then the annual ones, still this is pretty good for annual, but if you would go to the East Coast, generally they're pretty much decorrelated. So that's that image. So you can see there's quite some interferograms there. We can look again at the average coherence. Didn't really change very much between the previous one and this one, which we have now. So it's they look pretty much alike. So statistically, I don't really think it has changed very much, the behavior. And then also, if you look now in time, you can see there is many more pairs. The plot becomes a little bit illegible, but if you would open up the EPS figure, then you can zoom in and zoom out. But the PNG doesn't, of course, it doesn't have that. So that is the spatial temporal considerations notebook. Are there any questions?
Could you please get back a little up to the to qualitative plots?
Sure.
Yeah, this place. Yeah, exactly here at this cell in area plots. I'm just it's just giving me an error that the index is out of the list and giving the same error.
Could you copy it in the chat, and perhaps we
I'm using another PC, just that's why I cannot copy and paste. Let me see if I can connect with this one.
Okay. I mean, we can definitely follow up offline and get it to work for you. Did you change the kernel to the right kernel? I guess you did, because it was a different error message.
By the way, we do have breakout rooms, and people can go off there and work on things separately.
Okay.
And be also done during the office hours if there's one specific problem that's only for one person. So
sounds good. Okay, yeah, so let's do that, and definitely we will help you there. The other thing which I briefly wanted to touch upon is the preparation to time series processing, and that one is not in the notebook from Paul. So if you go under area tools, to Jupyter Docs, there is a notebook which is called Area TS Setup. That one is the one which you would run just ahead of MinPy. So technically speaking, there's only 2 area tools programs that you need to call. Area download to go and download all your products, and area TS setup. And TS setup is like I said, it's making sure that you have stitched the products and cropped them to the same box and packaged them up into a format which is compatible with MinPy. But really the operations which are being done is that area TS setup is doing area extract over and over again underneath its engine on a modular level. So that's why it's very important to be familiar with the extract one to kind of know what is happening. So again, you can use the stage data for now. I think I had already executed this myself, so I'm not going to redo that. Again, you would change the kernel to UNAVCO. And this gives you a zoom again over the San Francisco area, track 42. A lot of the commands in area tools are the same across the different programs. So again, area download, we have already done that. You can do TS setup, but if you look over here, the image file, the word directory, the layers, the DEM, the projection, the bounding box, the number of threads, etc., the crop to, all these options are the same. So you should be able to just reuse the same steps which you have done before. So let me just jump directly to the TS setup. So as part of what you need for MinPy processing, we provide a water DEM. We need the coherence files, the unwrapped files, the incidence angle information, like the line of sight information, like the incidence and the azimuth, as well as the perpendicular baseline are needed for MinPy processing in the DEM. So all of these things are done already through this program on the fly for you based on that bounding box. So it takes some time to execute. We noticed that there is a lot of additional screen output which somehow sneaked in, but in an earlier version it was just giving you this progress bar. So we will clean that up in the next release, that it doesn't output all this intermediate information anymore, and it will just it would be easier to track for you the changes, not in such a convoluted way. But in the end, once that has done, we have, let's say, stitched a single interferogram and cropped it. We do that for all of them. Then we package them up into a VRT stack. And that VRT stack is just it's a single file which has a bunch of file pointers to those individual files, which are still NV files. If you would have used the virtual data processing option, it's getting a little bit more complex, then you would have that merge stack. It would actually point with a VRT to another VRT, which would point to the online buckets in there. Only the rasters, which actually get written out and modified, like the unwrapped phase, those would have been written out still because you're manipulating the layer. I suggest you to look at this in your own time as well. And I know that Yunjin will have some stage data for you as well to use. So let me go to the one which actually ran. To see if I can show you the plots. Okay, good. Yeah, okay, good. So I actually ran this one here. It will by default duplicate, remove duplicates. We have some duplicates from different versions, so that's handled all internally for you already. You can then plot, let's say, the water mask by looking at the /mask folder. There's a water mask, and there's functions provided to plot them up. But again, this is the 0 is the water, the 1 is the land. So you can here see the San Francisco Bay Area, the San Francisco area, and this is the Bay Area. The Golden Gate Bridge would be over here. So you can see that up here. Then the water mask gets by default applied to the interferograms. So here you can see one of the interferograms. So there's an unwrapped phase folder where the stitched interferograms are provided. And you can see that this image, and I think it was a question before, which I've seen, doesn't really contain much tectonic deformation. It's predominantly atmosphere. So you can see these nice rolling waves of tropospheric noise. When you see these kind of more red dottish or blue dottish, that's really areas which are more decorrelated in here. We can also look at the DM that's provided over here. We're actually using OpenTopo, and we're using their API to stitch to them and prepare that in the same spatial extent as well. So as I said, it makes stack files. Once it has done that for all the files, a coherent stack, a connected component stack, and a wrap stack, which if you would look in that, and you do gdal.info, you just see it points to all these other VRTs. So this file is of magnitude 0, right? It doesn't have anything really in it because it's all virtual. But then if you would go and look at this VRT, it points to an NV file. So you can do the same for the unwrapped phase. You could actually go and plot them, and you can say plot the first band, and that would open up the very first interferogram. So that's shown over here again. So that was kind of in a nutshell. If there is any questions, I could try to answer them.
Yeah, it's actually, from my perspective, it's a little confusing. Previous years, I think we had a more coherent approach, but because we rearranged the modules, we only trained on a portion of them. So the sort of a sequential process you went through before is not there as well as it used to be. It could be just me, not the rest of the student body. But it might be good for the office hours and maybe 10 o'clock tomorrow, just to have a short summary of the step-by-step part, not going through a notebook, but just like a list of do this first, then do this, then do this to get.
Yeah, so generally, indeed. So if I would do it, then you wouldn't have done it before. I would just go notebook by notebook. I would do area download first, then I would do area extract, then I would do area plot, and then area TS setup. So currently, we did really we only covered the plot and the TS setup, which are really the two final notebooks. There's a lot of valuable information, area extract, which really explains you more step by step what is in the product, how it is formatted, what are the layers, what is the procedure for stitching, and talks you to all the different scenarios of cropping and stitching. So definitely the area extract, I think that is a core part.
That's the homework. That's the homework for tonight, right?
Yes, that's correct.
Yeah, so maybe, thanks for explaining that. So maybe the process would be that everybody does the homework, and then tomorrow at 10, when we go over the homework, we would answer questions related to that, because that's sort of key to it.
Yeah.
Okay, that sounds good.
And I saw that some people were asking if we can add more products. Email you your region of interest. We are definitely scaling up over the next few months. We will be adding in the full Aleutian volcano chain, and we will add in most of the West Coast, and we are targeting to do the Tibetan Plateau over the next few months as well. And then Arabia is being added to. So we're expecting the archive to double or triple over the next year. Thank you.
Yeah, good. That was very efficient. So we're basically back on track. I see Brian did figure out how to get into the Zoom, so that's great. We're all set up for that time. I guess we could, if there are no further questions, we could take a break for 10 minutes and then start up at 1. There's a question there. ICE results should go through the ARIA tools before MintPy. Go. So maybe somebody should explain that a little bit more. So ICE produces unwrapped interferograms, and ARIA tools or ARIA has already produced those unwrapped interferograms for you. So at some level, depending on the processing parameters, those are equivalent. So you would either run one or the other.
Yeah, Paul, maybe I could add a little bit more to that question.
Yeah.
So ICE, as you can see, has a lot of applications. It generates pairs of interferograms. It also has another component, which me and Harish will demonstrate tomorrow for the stack processing. So if you use the stack processor in ICE, then your result will be directly loaded into MinPy. And ARIA is using ICE in the core for the processing, the pair ones. So ARIA is generating the pairwise interferograms. They are co-registered, but different interferograms are not co-registered with each other consistently in space. So that's why we need ARIA tools to crop all of them in the same spatial coverage. So basically, ARIA tools is helping the ICE pairs by pairs interferograms into a similar fashion as the stack processor in ICE.
Oh, so you're saying then that for the ICE products, do they also need to be run through ARIA tools for cropping, or?
If you are using TOPS app or ScriptMap app, yes. Similarly, not directly. I'm not sure if it's supported by ARIA tools. If you're using the pairwise or TOPS app or ScriptMap app that we learned in this course, you need to crop it. If you're using TOPS stack or ScriptMap stack that we will demonstrate tomorrow, which in core is also using the two apps, then no, you don't need to. I remember last year, Harish has a very nice figure in PowerPoint to show the relationships.
Okay, so you could run the ICE processor pairwise to produce pre-cropped data for all of your pairs, I assume, or not.
I'm sorry, give me a minute. Let me just bring up a figure that Harish had before. So this is so what we have learned so far. We always started from SLCs. I'm just focusing behind that. Let's just forget that for now. Can you hear me?
Yeah.
Okay. So what we have learned so far, either using TOPS app or StreetMap app to generate pairs, to generate one interferogram from a pair of SLCs. And then, of course, for time series, you need a lot of pairs, so you can just replicate this process a lot of times. Then you will get a pairs of SLCs. But the pairs of SLCs, they either they're geocoded or not, they're within one interferogram, two SLCs, they are co-registered with each other, but between interferograms, they are not exactly co-registered with each other. So that's why when you have just using pairwise processing and you get a lot of pairs of interferograms, they are not strictly consistent in space. So that's why you need some cropping and stitching. And this blue box is what ARIA tools is doing. ICE also support the stack processing, which what it does is instead of two SLCs, it co-registered all SLCs into one common reference. And then once you have all SLCs consistent in space, then you can just do a multiplication to generate a lot of interferograms. And all those interferograms will be consistent with each other. And that's directly can be input into time series analysis. And that is what MinPy is doing on the orange box. So what ARIA and LIXAR or HiP3 from SF is implementing this box. And tomorrow, me and Harish were demonstrating this part. And we will go over the time series analysis tomorrow too.
All right, so I think I understand what you're saying, but maybe I have a fundamental misconception. If you geocode all of your pairs of interferograms using the same
bounding box,
the same DEM, then
yeah,
they are already co-registered and cropped properly, right? In ICE, if you do that in ICE.
Right, you can do that too. Yeah,
okay.
That's also perfectly fine.
Yeah, okay, that's where I was confused.
Yeah.
So there's lots of options. All right, we should take a break now, I think, before Brian starts. Maybe let's take a 9-minute break. So that now it's 8 minutes. So we'll just start at 1:05. Are we ready? You there, Brian?
Hello, I am here.
All right. So unfortunately, I have to go myself, but everybody else is here. I'm sad to miss your lecture, but it's going to be recorded so I can watch it later. So Brian is at MIT, he's on the staff of Brent Minshew's group. And Brent volunteered to do this, and Brian got to do it for him. So thank you so much, Brian, for doing this. I went through your notebook. It looks pretty interesting. It's too bad the data's not staged yet, but I think it'd be a good exercise or maybe final project for the group to replicate what you're about to show. So I think everybody will be listening intently. I'll turn it over to you, and I'll see you all at office hours this evening. Talk to you later.
All right, so let me go share my screen. Okay. So yeah, thanks for having me here. And I'd like to share with you a different use case than the one that you've all been talking about for the last few days, which is looking at what's called dense offset maps. So as opposed to InSAR and interferometric phase, which gives you probably the highest quality measurement of displacement that we can get from radar data, we will use what are called dense offset maps, which is a different kind of calculation. And we'll tend to have different applications and use cases. So before we start, as Paul mentioned, none of this data is staged. So what we're seeing here in the notebook are outputs that I've pre-run on a different computer. So don't go running ahead and try to execute any of the code cells because they won't work, at least the ones that are related to shell commands. So anyways, as Paul mentioned, I am now currently working at MIT with Brent Minshew, and our group primarily looks at velocity maps for glaciology applications. So that's where we use a lot of these dense offset techniques, because that's basically the only thing that works for things that move so fast, like glaciers and ice streams. But there are a lot of also other applications for using dense offsets, and I'll discuss those later on in the notebook. So a quick overview on what do we mean by dense offsets, and what's the math underpinning this dense offset operation. Well, basically all it is cross correlation, 2D cross correlation, which itself is a generalization of 1D cross correlation. And so when 1D cross correlation or discrete convolution, and essentially what you have there is you're trying to compare two signals. And in this case, you have a reference signal, looks like a rectangular pulse in blue, and you have a template signal, and you're trying to locate where those two signals overlap maximally. And that's the cross correlation operation is just a multiplication of these two signals. And so by sliding this template signal over varying shifts, you can compute your optimum shift between your two templates, between your template and your reference. And so if we look at this in 2D, just as a little cartoon, what we're seeing here is, let's say we have a reference patch, which is this larger patch here. And now we have a template patch, which can come from an image from, let's say, a different date. So our reference date, just like we do with InSAR pairs, we have two images with different dates. And in this case, this is an optical image, but we have a reference patch and a template patch, and we want to find where within this larger reference patch, this template patch is most optimally aligned with the reference image. And so what you do is you slide this template patch over in 2D over multiple locations, and which is what this cartoon is showing here. And what you get is you get what's called a correlation surface, which is essentially a 2D grid that computes the correlation sum, because the correlation is just a multiplication. So it just computes the multiplication between two patches at different points, and where they're most aligned is where you get a peak in your correlation surface. So that's a quick, that's like a cartoonish view of what's going on, and we'll actually look at this in more detail. We're going to look at two actual image patches, and we'll look at that a little bit closer later on. So that's essentially how you compute a displacement between two little image patches. So this displacement, is equivalent to, let's say, your InSAR phase. But what you can get with this displacement is you can get displacement in both the range and the azimuth directions, or the X and the Y direction. And so in order to make a map out of this, it's pretty simple. All you have to do is you just repeat this operation in an embarrassingly parallel way over your entire image. So here in this cartoon, I'll say you have a background image of a glacier, and you're going to repeat this 2D cross correlation at each one of these rectangles. In actual practice, these rectangles can be either right next to each other, or they can even have partial overlap. So you're kind of reusing some of the windows. But what you get out of this is a map, is a value of offset at each one of these rectangles, and then so you can get a map of dense offsets that will look, something similar to InSAR phase. So in ICE, when we're going to look at dense offsets, we're going to look at it within the context of topsap.py. But you can actually run dense offsets with any two co-registered pairs, such as with a strip map app, or any pairs within TopStack. And I'll mention TopStack a little bit later. But in ICE, we're looking at it in TopSap. And what's done is that we're doing this 2D cross correlation on reference and secondary SLCs. So it's done in full resolution, and the complex data are first converted into magnitude images prior to the cross correlation. So there actually is a way to do the cross correlation with the complex data. So in effect, you're using the phase information. But I believe in the way it's currently implemented, at least within TOPS mode, and as well as in strip map mode, is that the complex data are first converted into magnitude, amplitude images, and then prior to the cross correlation, and then you create your dense offset map from there. So in addition to the dense offset map, ICE will also provide correlation signal to noise ratio, which is always important to have, and covariance, where the covariance of your estimate of your maximum shift, that's actually computed by computing the curvature of the correlation surface. So once you oversample this surface, it'll have some level of curvature, and so you can imagine the sharper the peak of your correlation, the less uncertainty you have in your shift. So real quick, I did want to mention what are the advantages and disadvantages of dense offset maps, and particularly when compared to InSAR phase, since InSAR phase is what we're more used to, and it's what we've been discussing mostly in this workshop. So dense offsets, I'll start off with the good news. The dense offsets, they are useful in situations where the ground or surface displacement is really large between two acquisition dates. So you can imagine within a glacier, let's say it's moving 2 meters per day, and you have a repeat time of 6 days or 12 days. Now you're looking at a displacement of 12 meters, 20 meters, 30 meters, just within a pair. And so you're going to have a very hard time trying to co-register your images properly in order to do InSAR. And what you'll see for the most part is that your phase will be completely decorrelated. You won't have any usable fringes when you have very fast moving regions. In other scenarios, let's say really large earthquakes where there's really large ground rupture close to the fault, the pixels just move too much in order for you to create anything usable within an interferogram. But luckily, you don't have to throw that data away. You can use dense offsets, because all you have to do is track the motion of one pixel, of one little reference patch, to a different location in your second scene, your secondary scene. And as long as the surface properties haven't changed too much between those two dates, so like if vegetation hasn't been removed, or in the case of glaciology, if there hasn't been a snowfall event, then you can track coherently the motion of each one of these pixels, or each one of these sub windows, and so you can recover you can recover those displacements when the displacements themselves are too large for InSAR. Another advantage is, as I mentioned before, is that dense offsets, they automatically give us displacement in 2 directions, range and azimuth, which is nice. So, you know, if you're doing anything like a physical inversion, that's like a earthquake fault slip inversion, finite fault model, or a volcanic model, it's already good. You want as many look directions as you can get. And so by automatically getting it in 2 directions, that'll help you constrain your models much easier. Whereas InSAR by default will only give you phase changes in the range direction. And also the dense offset operation is really general, and you can see it being used on any pair of co-registered images. So you can use it on Landsat, you can use it on Sentinel-2, MODIS data, anything where you have co-registered images. This could also be in geographic space. And I've also seen it being applied to things like pictures, like if you can take pictures of a glacier just off to the side with a camera that's fixed, and you can take a time lapse of a glacier. And by tracking the motion of sub windows in exactly the same way, you can compute a glacier velocity from the perspective of your time lapse camera, which is pretty cool. So obviously the main disadvantage of offset maps is a much, much higher level of noise in the measurements as compared to InSAR phase. So courtesy of Eric Fielding's Twitter post recently, I think he computed this InSAR phase for the very recent magnitude 7 Haiti earthquake. So you see InSAR phase on the left. You see nice, beautiful, very clean measurements of essentially strike slip motion. If you compute that using offsets, you can see you get pretty much the same pattern of displacement, and the same sense of motion, basically the same magnitude of displacement, but it's obviously a lot noisier. But if you look closely, you can see in some of these areas, let's say very close to the fault, you lose a lot of InSAR phase, most likely because the ground motion is very high. But if you look at the dense offset maps, you can see you actually get usable measurements of ground motion in those areas. So this is a nice demonstration of, when all else fails with InSAR, you can always turn to dense offsets to get some of those measurements back. And in general, this kind of comparison is only valid if you're able to get any kind of InSAR phase at all. If you can't get any InSAR phase, which is the case for most of our use cases in glaciology, then dense offsets are the only thing that you can do. So
there's a question in the chat.
Yes.
Saying what's the precision or the minimum observable movement of these techniques, this image matching?
Yeah, that's a good question. And I don't have that number off the top of my head, but it would probably, so if you have, it will be some fraction of your pixel size that you're using to do the cross correlation. So if you imagine in full resolution, your SLCs for Sentinel will take the upper bound 14 meters in azimuth, then, at best, you'll get somewhere probably around, 10 meters, 5 to 10 meters in precision in your offset measurement. But that's at best as your lower bound. But, as you get, more noise sources in your images, you'll start to see that noise floor start to increase a little bit higher and higher. So, rule of thumb, it's kind of, think about like half a pixel is roughly where you'd see kind of your precision. I wouldn't expect anything much lower than that. With InSAR, you're down to the centimeter level. But yeah, so somewhere around there.
I've managed to get for Envisat, I got maybe 1/10 of a pixel.
Oh, really?
Yeah,
well, that's good
for
to know,
earthquakes though, not for
yeah. Okay, well, 1/10 of a pixel. So just oversample your image to make your pixel really small, then you're good to go.
You can, you can calculate theoretically how good you can get with this, and it's at a fraction of a 1/10 of a pixel range for good conditions.
Okay. Thank you.
The holy grail would be to get good enough with the offset tracking so that you don't have to phase unwrap anymore. So get within the 1 fringe accuracy, and you can actually, and the limit here is resolution, so you'd have to have a really wide bandwidth sensor that supports very, very high resolution, and you could potentially close the loop between offsets and fringes, which could be really cool.
Yeah, that's a great point. And you can kind of see that when you apply dense offsets to really high resolution images. Like, so if you look at if you do this on Cosmos SkyMed spotlight images, or even Terrace RX images, or let's say you have optical data, like let's say from Planet Labs, that's about 3-meter resolution. You can run these kind of offset calculation, and you can get really beautiful displacement maps from those. So yeah, if you had high resolution data, whether it be radar or optical, then it's worth trying this out to see what you can get. So in this case, our study area for this notebook is Pine Island Glacier in West Antarctica. It is a very fast flowing ice stream responsible for about 25% of the mass loss from Antarctica. So it's a high target area for sure. And I took a Sentinel frame, path 65, frame 906. And we're going to look at 4 different dates in January of 2020. And so from these 4 dates, we're going to generate 3 separate maps of dense range and azimuth offsets using TopSat. And so from this preview image, we can see that the fast flowing parts of PIG are basically in swaths 2 and 3. So we're going to tell TopSat to process only swaths 2 and 3. Also note that this is an ascending pass. So here's the flight direction. Additionally, we'll use for the digital elevation model, we're going to use the reference elevation model of Antarctica, REMA, which you can find here. And we're going to extract 2 different subsets for processing, 1 for processing and 1 for geocoding, which will be a little bit tighter. So for TOPS processing, you've already gone over this before. And I'd like to remind you that the code below that does the actual TOPS processing won't work because this data is not on OpenSAR Lab, but you can obviously apply this code to your own data and any other data that you have and play along there. So in this case, the way I've set up my processing working directory is I have all my raw data are in this file, this directory called Vertex. And I put all my orbit data in orbit, all the auxiliary data, calibration data in aux. And we're going to look at pairs 1 by 1 in these 3 separate working directories. So as we've just recently discussed, you can take this approach and then use ARIA tools to ingest these things into tools like MinPy, or you can process things in top stack mode, which would be quite a lot more efficient when you have a lot of SLCs. But here we're going to do it pair by pair using TopSat. And so the key thing here is for running TopSat for targeting dense offsets, there are actually a lot of steps that we can skip. So TopSat, has all these amazing tools to really precisely co-register SLCs and correct for phase artifacts at burst boundaries, and so getting really good co-registration. So your phase is the highest quality possible. But here we don't care about phase at all. So you can actually skip a lot of those steps, and so which would speed things up quite a bit. So here's an example configuration of my TopSat file. As I said before, processing swaths we're only processing swaths 2 to 3. I specified my 2 DEMs here. And here's where I unset all the InSAR processing steps. Do interferogram false, do ESD false. No unwrapping, there's nothing to unwrap. No sense in doing an ionospheric correction because the phase will be just pure garbage anyways. And then there's nothing to geocode. But I will note that, as I'll make a final note at the end of this notebook, is that if you want to rotate your range and azimuth offsets to, something like east, north, up, or east-north in terms of like horizontal displacements, then you'll need the geometry files like lon.rdr, lat.rdr, and los.rdr, which basically tells you the orientation of the radar for each pixel. And so in order to do that, you have to set do interferogram to true. This is kind of a little bit of a hack. You have to set do interferogram to true and then rerun geocoding. Or actually, I would set do interferogram to true, set this geocode list, and run all this, keep all these to false, and then just run topsap like normal. And so here are the parameters that you can tune for doing the dense offsets, various window sizes, skip width, skip heights. And to help you understand what each one of these parameters mean, I made this little schematic here. Basically, the window width and the window height tells you how big each sub patch will be in your reference and secondary images. Some things to consider are that larger windows will give you a more robust, or could potentially give you a more robust offset measurement with lower noise. But if your window width is too large, then it's possible that you can get some displacement within your window. Like let's say in the worst case scenario, your window width is your whole image. Then obviously that's not going to work because there's so much motion within your window. So you'll tend to see window widths around like 64 by 64, in which case, the motion is primarily rigid body motion of your window. So
Brian, could you increase your zoom in a little bit?
Oh yeah.
Thank you.
How's that?
Great.
A little bit better?
Yeah.
Okay. Yeah, and you can actually pull up this notebook. These things will be rendered in the OpenStar lab. So if you want to take a closer look, I invite you to do that. So yeah, you have window width and window height, and skip width, skip height essentially means how many pixels between neighboring or adjacent subpatches. So the smaller the skip width, the more number of pixels you'll have in your offset image. And then also search window height and search window width. This essentially says how many pixels to the left to right and up down of my reference image do I slide this template image. So this will essentially be set by what you expect the magnitude of your displacement to be. So if you expect it to be maybe 10 pixels, then you can set a search window width of maybe like 20 on each side. If you expect it to be really high, then you might want to increase that search window width just to make sure that you're able to actually capture that peak in your correlation surface. So these are all things that you would want to kind of play around with your own data. And it's obviously going to be data dependent because each SLC type for different sensors will have their own resolution. So window widths will mean different things for different SLCs and different sensors. So these are the XMLs for the specific scenes, nothing crazy there. And so here I'll show you the output for one pair. And this just tends to be the way I like to run things. I like to run topsat from startup to verify DEM, just to make sure all my input files are in order. In this case, this step actually catches a lot of errors on my part, like whether or not I've put errors in my configuration file, or typos in my XMLs, or my DEM doesn't have the right format. This catches a lot of those errors. And so I like to run this first. And then I run from topo to geocode. And as a reminder, a lot of the InSAR steps are set to false with the way these are set up now. So this should run faster than you would with normal topsap if you're doing InSAR. So that's another minor plus to this workflow. So once you get to geocode, you essentially have two co-registered SLCs for your reference and your SLC image, and that in your secondary image, and now you're able to do dense offsets. So before we run the actual dense offsets implemented in ICE, I want to take a closer look on the actual what's going on within this operation, and we're going to look at a single pair of patches. So I pre-extracted some patches from these SLCs, and these are actually on OpenStar Labs, so you can actually run these if you want to. And so these are two patches somewhere within the middle of the ice shelf. And I took about a 128 by 128 patch for both. And the reference patch has a 20 pixel buffer, which acts as the search window. I'm going to remove the mean from each patch, and I'm just going to plot it. So you can see we have a very small little zoomed in view over our ice shelf. And you can tell that these are pretty much over the same area, that they're co-registered. This is actually a little bit smaller than this one because of the search window buffer. But now the task is to figure out, all right, what is the shift between these two patches? Because we do expect motion because Pine Island Glacier is moving very fast. So there should be some shift between these two patches. So to do the demonstration of this cross correlation, we're going to use a match template function implemented in OpenCV, which essentially does the same math that dense offsets does. And so an interesting point here is that this match template function is used within this project called AutoRift, which is also a JPL project. And they use AutoRift to essentially run these OpenCV offset estimation, over, well, in this case, AutoRift for the ITS Live project, they use it to measure velocities over all terrestrial land ice over the globe. So they made it to be very efficient as well. So that's another thing to play around with if you have the data and co-registered SLCs. I invite you to take a look at AutoRift as well. So we're going to use the match template function to essentially create a correlation surface between our reference patch and our secondary patch. And so all this code is essentially just bookkeeping. It's basically keeping track of where my reference image, my template or secondary image is within this little search grid. And what you get out of template matching is this 2D correlation surface. So this is an actual 2D surface of this cartoon that I showed above here. And what we can see from this surface is that if you take an argmax of that correlation surface to find a peak, you can see that the integer shift says that the X offset is about 0. So basically no shift in range, but there's actually about a 3 pixel shift in azimuth. So 3 pixels in azimuth. I believe I looked these down. So either way, it's already more than about 10 meters, 10 meters in displacement between these two pixels. So you could stop there. You could say, okay, I have an integer shift of 0 and 3. Now I can repeat this over my whole image in order to get a map of integer shifts. But we can actually do better by computing the sub-pixel shift. So in the discussion we were having a few minutes earlier, you can actually oversample this correlation surface to then, so you can imagine, let's say you have, you're doing some kind of polynomial fit to some coarse points. And if you do a good enough polynomial fit, you actually increase your resolution where you can find the peak of your polynomial. And so the way ICE does it is that it does the oversampling in the frequency domain. So it takes a 2D FFT of this correlation surface, of a sub window of this correlation surface, then you can oversample that, and then it finds the peak of the oversampled surface. So what we're going to do here instead, just as a demonstration, is we're going to take a sub window around this correlation peak, and we're just going to use simple interpolation implemented in SciPy. So in this case, so we find the peak, we take a little small window around it, and we call this SciPy function called ndimage.zoom, which just essentially oversamples it by a factor of 16. And so from there, we can then find the peak of the oversampled image. And that is what's being shown here. So on the left is a sub-window centered around our correlation service that we computed with match template. You can see that our peak was at 0 and 3. And now that we've oversampled it and find the peak of the oversampled surface, we can get a fraction of a pixel for our offset estimation, in which case we've estimated a range offset of -0.1 or -0.2 pixels and 2.6 pixels in azimuth. So of course, there's a question whether or not you trust this oversampled surface, but there are many different ways to do the oversampling. I believe AutoRift does Gaussian pyramids to do the oversampling. ISCE does the FFT oversampling, FFT-based oversampling. But in comparisons with InSAR phase, it seems to be pretty reliable, at least when you can do that comparison. So this is really kind of just a toy example of what's actually going on underneath the hood of dense offsets. So let's go ahead and run dense offsets. So in this case, we'll run start equals dense offsets and the geocode offsets. So this will include the offset estimation, filtering of the offsets, and then geocoding into latitude, longitude. And so once that's done, you would, if you ls your merge directory, you'd see all these files called dense offsets. And so here's all the stuff that you want to look at. And I've created a little helper function called plot offsets. You can find it in the file utilities.py. You can read through that. I won't go through it now, but it essentially plots the offsets on top of a Landsat image, just to get a little bit of context. And so here on top is the rate of change in the range direction. So I've scaled the offsets to go from offsets in pixels to meters and then meters per day by knowing the time separation between the pairs, which is 6 days. And so then you can kind of compute that into essentially a velocity, but I didn't call it velocity here because I'm restricting velocity to physical coordinates like east and north. So here I'm just calling it rate of change in the range direction. And here's the rate of change in the azimuth. So you can see that if you remember, our flight direction is this way from kind of a southeast to northwest. And so a good way to do a sanity check is to look at the sign of your offsets. So I believe the convention here is that your delta measurement is your secondary minus your reference. So in this case, the Pine Island Glacier is flowing this way in the same direction as the flight path, southeast and northwest. And so you would expect a change of azimuth, a negative change in azimuth between the two dates. So this essentially is showing that most of the motion is along the flight path direction, but you do get some pretty large range offsets as well, especially in the grounded ice, as you get a little bit of a bend in the glacier, a change in direction. So that's for one pair. And basically for the other two pairs, the steps are exactly the same. In this case, I change to the other directory, do the same thing where I do my pre-processing and then run topo to geocode, run the offsets, plot the offsets. They look pretty much the same, which is what you'd expect because this pair is only 6 days later. So you don't expect too much change. And basically the same thing for the third pair. Run TopSap, plot your offsets, and now you have a third set of offset measurements. And so this last part, I want to talk about how so then how you would use these offset maps to make a stack. So, I mean, they're going to be much more sophisticated stack tools presented tomorrow with MintPy and TopStack to prepare data and to go into things like MintPy. But here is just like, I'm going to create a little 3-element stack just to kind of show you kind of how you do things. In which case, what I'm going to do is I take the geocoded offset maps for each one of these pairs, and I basically resample it to a common window. So it's essentially a generalization of resampling or cropping, resampling, and basically just cropping and resampling. So actually, if I go into this create stack function here, and if you go down here to the bottom, you can see for each file, what I do is I open it with GDAL. I load the offsets, read the offsets, and I call GDAL translate. So this GDAL translate basically says I want to resample everything into this projection window. So everything will have the same projection window. They'll all be in the same geometry. And I can essentially create a new data set in memory by calling GDAL translate on my offsets. And so now everything will be aligned in space. And so then I create a stack for my azimuth and my range offsets, in which case the stack is now a 3D array. And you see the stack shape is 432 by 2878 by 3, in which case 432 is number of latitude grid points. 2878 is number of longitude grid points. You can see there's a very large asymmetry here because we're in the poles. Traditionally, we don't use latitude and longitude in the poles. We use like polar stereographic projection. But in this case, we're using what's directly output from ICE. And then 3 here is my number of time steps, in which case just 3 because I have 3 pairs. So I created this stack. And let's look at a time series. Let's look at the most boring time series you'll ever see here at this row and at this column. So I'm going to extract the time series from that row and column, and let's plot it up. And you can see we only have 3 points, and not much is happening. There's very little change, and now you're seeing basically the noise within this little 12-day window. Essentially, the velocities are roughly constant for this 12-day window. So what you can do once you have this this stack data is you can fit a time series model. I believe the MintPy will in the discussion with MintPy they'll go into much more detail on fitting time series, but in this case I'm going to fit again the simplest time series model you can think of, which is the mean. So the mean is equivalent to a 0th order polynomial, right? So I'm going to compute the mean of this time series by just using pure NumPy. Take the mean of the stack along the axis number 2, which is the 3rd axis, and then let's plot it up. So this is a nice. This was traditionally a nice use case for InSAR stacks back before we started using it for more complicated studies. You stack a whole bunch of interferograms and you compute the mean. And this was like a couple decades ago. So you compute the mean, and then you get actually a much cleaner velocity map from that. And so in this case, we can compute the mean and plot it on top of our Landsat background. And here we go. So this is now our 0th order time series model for range direction and azimuth direction. And it looks basically similar to the offset maps that we made here. You could convince yourself it's a little bit cleaner, but that's a really quick introduction to using offsets to make a stack. And so just to whet your appetite a bit, I want to show an actual velocity time series over Pine Island Glacier using these same techniques. In this case, we didn't do it, but Ian Jochen at the University of Washington, who's been doing this stuff for a long time, as part of the NASA Measures project, he did this stuff using a combination of Sentinel data and TerraSAR-X data over the Amundsen Sea sector. And so for this same point that we plotted here, days since 2020, here's what that offset map would look like. Well, those offset maps converted into monthly velocity maps. Here's what that would look like over a much longer time span. And you can see in 2020, we're basically smack dab in the middle of a large scale speed up event at PIG. And what you can do then is you can start applying a little bit more sophisticated time series processing tools where you can decompose the signal into long-term and short-term variations. So that's what this is showing here, so that we have a long-term trend in this upper line, and we can have these shorter-term seasonal variations. So you can see that there's actually a little bit of some seasonal modulation to the velocities over the ice shelf here. So once you apply these kinds of techniques over your whole image, I believe Brent showed this movie yesterday, is you can actually get a really smoothly reconstructed changes in velocity in response to things like large calving events over your entire image. So that's where you really start to see the power of combining offset maps with stack processing techniques. So to end it off, we do want to mention a few other additional topics that you would need to consider before you start to use these techniques for your own data. The main thing is that the range offsets need to be transformed into geographic coordinates, east, north, up, because right now they're in range and azimuth. While convenient, they're not actually useful if you're trying to do like a inversion. So azimuth offsets themselves are only sensitive to the horizontal displacements. But as you know, the range offsets are just like a noisier version of InSAR phase. So they will also be sensitive to vertical displacements due to the incidence angle, non-zero incidence angle. So in glaciology, what we often do to kind of simplify these things is we assume surface parallel flow, which essentially means that you can use the surface slope of your glacier to simplify the reconstruction of your velocity components. So you can actually solve for east and north components from range and azimuth. But you can not assume that. And if you have range and azimuth offsets from, like, say, descending and ascending passes, then you essentially have 4 unknowns, or 4 observables for 3 unknowns. And then you can solve a pretty simple least squares problem to recover your east, north, and up components. 2 other things. It is important to quantify these uncertainties, and luckily ICE provides dense offsets _ covariance. So I would always recommend you to look at these covariance and SNR files to get a feel for which offsets are more reliable than others. And then you can propagate these uncertainties to any of your components in geographic coordinates. And then, of course, as I mentioned before, it's always important to play around with your offset processing parameters, especially window size and your search window size. So like I said before, your window size could basically make or break the quality of your offsets. So make sure to play around with that with your own data. And with that, I'm happy to take any questions. I guess let's see what there are some messages in the chat, or if you have any questions, you can just speak out loud. If you're trying to capture motion at the lower bound of observable motion, yeah, in that case, I would increase. So this is Forrest Williams' comment. If you're trying to capture motion at the lower bound of observable motion, what window size would you recommend? I would recommend a larger window size, so you can beat down the noise and you don't have to worry about intra patch displacement. So maybe somewhere around 128. I think since Sentinel has the range pixel was much smaller than the azimuth pixel, I used kind of a rectangular window. but I would recommend, like 128 or even 256 if you think that there's not much motion. You should be able to see this notebook in the OpenSAR lab. You might need to refresh.
Yeah, I think we clarified that. If you can't see the
Okay.
notebook, you have to stop your server and restart it. The notebook was
Okay.
pushed last night, so if your instance kept on running, it doesn't necessarily have the latest set of notebooks in your system. I provided some instructions. I think one of the big blue box or gray box, I guess, gives some instructions.
Forrest is asking, what's your procedure for selecting window size?
Yeah. Start small. Start with the default 64 by 64 and see what that looks like. If it's noisy, maybe try increasing that 128 by 128 or 128 by 64, and just go for a range of window sizes and go from there. I would start small, go small to large, and then look at your covariance and your SNR, and then kind of see if you start to over smooth or bias out your offsets. Actually, if you go too large, you'll then go to the point where you're capturing motion within your patch, and you probably, I don't know this for sure, but you probably get a lower quality offset, and you would see a much larger covariance in that case. But yeah, start small and then increase systematically. What is the approximate? So the vector orientation for displacement is essentially just 90 degrees from your look direction in range. So, so if you have, if you look at your heading angle, that's essentially your azimuth orientation, and you can say your incidence angle is essentially flat along the surface. So that would be a 90 degrees incidence angle. That's kind of one way to synthesize converting your azimuth. That's one way to synthesize an azimuth look vector from look vector components that you have in range.
I'm slowly trying to download all the files to run the
Yeah,
notebook.
that's why I didn't put them on here.
Yeah,
it's so
sure.
large.
I get it. Where do I find the RIMA DEM?
Oh, that is, I had a link in here. Yeah, here you go. Here's a link
cool.
in here, and I used the 100-meter mosaic. So it's provided in strips and time dependent strips, or in 100-meter, 8-meter, 100-meter, and 200-meter mosaics. So in this case, I think 100-meter worked well.
Okay, I'll have a go.
How do you feel about RIMA DEM versus Copernicus DEM?
I have no feelings because I have not yet tried Copernicus DEM. It's definitely something on my radar, no pun intended. But I mean, RIMA tends to be what's used mostly by glaciologists. I don't think there's been a full comparison yet between RIMA and Copernicus. Do you have a sense there?
I feel like we've done, there was some comparison, I think that maybe Ian Jockin did for ISCE for the DEM selection, where he felt like they were pretty close, but I can't remember the details.
Okay.
We had a brief out, so I should know that.
Yeah, it's definitely something I'll be looking at in the near future. There are two other questions. Images are not corrected for baseline perpendicular. No, but I think that would be a pretty small signal. for these offsets? Maybe someone else can answer that for me or fill in. Yes.
Parvis, are you referring that in the previous lecture we talked about the phase? Phase has a topography component that is proportional to the perpendicular baseline. That is, if that's the case, then there will be inaccuracy from the DEM that will be propagated in the phase, and that same thing will also be propagated into the range offset. But that one, as Bram just mentioned, is actually very small compared with usually what range offset was measured, if I understand your question right.
Yeah, the noise here, as you said before, is the noise level will traditionally be pretty much be a little bit higher than what you get for the correction. And Alex had another question. Is there documentation on window size from synthetic tests to give some guidance on evaluating window size? How will I know if my window size is too large, too small? Unfortunately, I do not have documentation or good rules of thumb there. I would just say play around with your own data. Make a synthetic signal, shift it, use something like an FFT to shift it in 2 directions, and then run dense offsets on that, or run something like auto rift on that, and then you can get an intuition on what would be a good window size, because it really depends on the signal that you're trying to measure, whether or not it's large or really small scale or large scale. It will vary. So unfortunately, it's not a good rule of thumb other than just try it out and start small and go large for your window sizes.
There's a few optimizations you can make. I mean, the window size is one of them. If you look at ice caps, you probably are okay with a bit of a bigger window size for the cross correlation. If you look at narrower outlet glaciers or maybe valley glaciers, you probably have to go a little smaller. To avoid false detections, you usually feed the program with some sort of an expectation of how much motion you would expect. So you usually give it a boundary where you say, like, if based on your match, the motion is beyond a certain point, then just assume that it's a wrong match. So there's some way how you can avoid some false matches this way. And you can also control which pairs you use. If you have very fast motion, you may want to take image pairs that are very close to each other in time. If you're looking at smaller motion, you may want to give it more time so that enough motion can develop so that you can actually measure the deformation that you expect. So there's a variety of knobs that you can twist, and they depend a bit on your domain expertise, I guess, of the area that you're looking at.
That's right, yeah. And those kinds of things aren't built into the TOPS app flow, but I think AutoRift has some kind of that adaptive search capability in there, or otherwise you just have to code it up yourself, kind of just doing an extension of this code that I presented here. But yeah, that's when you're getting to expert level with the offsets.
Yeah, AutoRift is actually a funny story, because AutoRift, to run automatically and not have too many false matches, they do use a large sort of a maximum amount of offset thresholds to not get lots of false measurements. And it turns out that there's a glacier in Alaska that's surging like crazy right now.
Right.
And it surged so fast that AutoRift couldn't measure it anymore, because the amount of displacement they got was much larger than what AutoRift accepted. So
you got to update those hard-coded parameters. Yeah,
could bite you if you are too restrictive.
Yeah. All right. Yeah, I think that's about it. No, use JKim said, did I use this technique on the seasonal signal for LA Basin. No, that was pure InSAR phase, pure InSAR phase, and an assumption that all motion was vertical within the basin. So.
I'd have a quick question from sort of a geology perspective. There's probably, say, if you look at the Greenland ice caps, places where you would favor InSAR, places where you favor speckle tracking. Do you have some guidance on how what you use to sort of make that decision?
Myself, no, I don't have any good guidance other than seeing if you can get any phase at all. Well, obviously you have preformed velocity maps, and you can use that as itself as your a priori information on, do I expect any hope of getting phase here? And if I see my velocity is slow enough, then like you said, yeah, in the ice caps where velocity is low enough, then, and if I don't expect large precipitation events between my pair that would change the surface properties, then you can actually get decent phase. And actually, when I was building this notebook, I looked at a frame that was a little bit closer to the divide between Pine Island Glacier and Redford, so velocity was slow, and I was able to get pretty decent fringes over there. So as usual, I don't have any good guidance other than just try it out and see if you can get something. And if you expect to see something, then see if you can get something. If you know you're not going to get anything, then I wouldn't even bother.
Thank you. That was super interesting. Gareth, if you succeed at downloading the data, we could actually bake that into the S3 and change the notebook so that we can actually run through it with a data set.
I have the data. I need to do the ellipsoid correction for the DEM next.
Yeah, we're trying to update that, and at least on the notebook framework, Brian, we have the capability, if we have the data downloaded, which would take a long time, to deposit it in a Amazon bucket.
Yes,
it's easy to grab, and then maybe people can run through the notebook with an actual data set.
Yeah, I can try to upload the DEM somewhere.
Yeah,
I don't know the procedure for the S3 bucket. I don't have familiarity with that. I can send someone a Dropbox link if that works.
Right, that'd be great. And then Alex or can put it in S3, and then people can maybe have the data and run through it with the notebook.
Okay, I'll send it to Alex.
Any more questions? I think otherwise we are at the end of the session today. And if not, then, Brian, you're the first one of all people, maybe together with David, to end on time.
Oh, well, I saw 5 o'clock and I was like, uh-oh. I thought it was supposed to be, sorry, it's 5 o'clock, 5 a.m. my time. It's 2 o'clock. Yeah, well, there's a little bit of time, time in the beginning, but I'm glad.
Well, there is one more piece I think that we need to discuss. If David is still on, is David still on? Did he discuss what the homework is before he left?
Yes, he talked about the homework, which is the area extract or area exploit notebook. Someone, I believe students are aware of it.
Are there more questions for the homework? If that's not the case, then I think we can close for today. And we'd be back bright and early tomorrow for the last day. Awesome. Good to see you all.